Welcome to our comprehensive guide on colonizing Mars, where we'll explore everything you need to know about humanity's next giant leap. This journey is not just a dream anymore, but a tangible goal that scientists, engineers, and visionaries are actively working towards. Mars, the red planet, has captured our imagination for centuries, and now we're on the brink of turning science fiction into reality. Mars offers a unique opportunity for humanity to expand our horizons and secure a second home. Its similarities to Earth, such as the length of its days and the presence of water, make it an intriguing candidate for colonization. But it's not just about survival. It's about thriving in a new world and creating a sustainable future for generations to come. To understand why Mars is our target, we need to dive into its scientific allure. Mars's geological features tell a story of a planet that once had flowing water and possibly life. The planet's diverse landscape, from towering volcanoes to deep canyons, provides clues about its past and potential resources for future settlers. We'll uncover what makes Mars the ideal candidate for human colonization. Achieving the dream of colonizing Mars requires cutting-edge technology and innovative solutions. From the spacecraft that will take us there to the habitats that will keep us safe, every aspect needs meticulous planning and execution. We'll explore the incredible advancements in space travel, life support systems, and habitat construction that are paving the way for humans to live on Mars. Human health and survival on Mars present significant challenges that we must overcome. The harsh environment, with its thin atmosphere and high radiation levels, poses serious risks. But with advanced medical research and protective measures, we can ensure the well-being of future Martians. We'll discuss the strategies and technologies designed to safeguard our physical and psychological health. Mars's resources are crucial for sustaining human life and building a self-sufficient colony. Utilizing the planet's natural resources, such as extracting water and mining minerals, will be key to our success. In-situ resource utilization, or ISRU, is a game-changing approach that will allow us to live off the land. We'll delve into the methods and technologies that will enable resource extraction and management on Mars. Building habitats and infrastructure on Mars is a monumental task that requires innovative engineering solutions. From designing habitats that can withstand Mars' extreme conditions to developing transportation systems for moving around the planet, we'll cover the essential aspects of creating a livable environment. Join us as we explore the fascinating world of Martian architecture and urban planning. Energy solutions are critical for sustaining life on Mars, where solar power, nuclear energy, and other alternatives will play a vital role. We'll examine the potential energy sources that can provide reliable power for our colonies. Efficient energy storage and conservation strategies will be necessary to ensure a continuous power supply in the challenging Martian environment. Transportation on Mars will be an adventure in itself, with rovers, drones, and other vehicles enabling exploration and mobility. We'll take a closer look at the various modes of transport that will help colonists navigate the Martian surface, transport supplies, and conduct scientific research. Discover how we'll build a robust transportation network on the red planet. As we establish a presence on Mars, we'll also be building a new society and culture. Governance, laws, social structures, and cultural activities will shape the future of Martian colonies. We'll explore how these aspects will develop and the importance of creating a cohesive community. Mars colonization is not just a scientific endeavor, but a human one, filled with opportunities for growth and innovation. Mars's geological features are both intriguing and diverse, offering insights into the planet's history. The surface is marked by vast plains, towering volcanoes, and deep canyons that hint at a dynamic past. Each feature provides clues about the geological processes that have shaped Mars over billions of years. One of the most notable geological features on Mars is Olympus Mons, the largest volcano in the solar system. Standing nearly 22 kilometers high, it dwarfs any mountain on Earth. Its size suggests that Mars was geologically active for a significant period. Valles Marineris, an immense canyon system, stretches over 4,000 kilometers across the Martian surface. This canyon is up to 7 kilometers deep in places, providing a window into the planet's crust. Its formation likely involved tectonic processes similar to those on Earth. Mars also has extensive networks of valleys and channels, indicating that liquid water once flowed across its surface. These ancient riverbeds and outflow channels suggest a wetter and possibly warmer climate in the past. Understanding these features helps scientists piece together Mars's climatic history. Impact craters dot the Martian landscape, offering a record of the planet's encounters with asteroids and comets. Some of these craters are well preserved, providing valuable information about the frequency and scale of impacts. The study of these craters can reveal the age and composition of the surface. The northern and southern polar ice caps are another significant feature of Mars. Composed mainly of water ice, these caps grow and recede with the changing seasons. They are crucial for understanding the planet's climate cycles and potential water resources. In addition to water ice, Mars has deposits of frozen carbon dioxide, or dry ice, particularly at the poles. These deposits expand and contract with seasonal temperature changes. They play a role in the planet's atmospheric dynamics and seasonal weather patterns. The presence of dust and sand dunes across Mars' surface is a testament to the planet's active aeolian processes. Wind shapes these dunes into various forms, creating a dynamic and ever-changing landscape. The movement of sand and dust influences the planet's surface conditions and weather. Mars's subsurface is of great interest to scientists, as it may hold clues to past life. Radar and other instruments suggest the presence of subsurface ice and possibly liquid water. Exploring these hidden layers could reveal more about the planet's potential to support life. The Tharsis region is home to some of the largest volcanic features on Mars. This vast volcanic plateau is thought to have played a significant role in the planet's geological history. The region's size and volcanic activity have implications for Mars's internal heat and tectonics. Mars' magnetic field, or lack thereof, is another important geological aspect. Unlike Earth, Mars does not have a global magnetic field, but localized magnetic anomalies exist. Studying these anomalies can provide insights into the planet's core and its geological evolution. The planet's crust varies in thickness, with the southern highlands being thicker than the northern plains. This dichotomy is one of Mars' most striking features and may have resulted from significant geological events. Understanding this variation helps in piecing together the planet's geologic past. Sedimentary rock formations on Mars, particularly in places like Gale Crater, suggest ancient lakes and rivers. These layered rocks can preserve the history of water activity and past environmental conditions. They are prime targets for exploration and the search for past life. Mars's surface is covered with a layer of regolith, a mix of dust, soil, and broken rock. This layer results from billions of years of meteorite impacts and weathering processes. Studying the regolith helps scientists understand the surface's physical properties and its potential for supporting human activities. Finally, Mars has several intriguing surface features that resemble those created by volcanic or hydrothermal activity. These include possible mud volcanoes and mineral deposits formed by hot springs. Investigating these features can shed light on the planet's volcanic history and the potential for past habitable environments. Mars's climate and atmosphere present unique challenges and opportunities for colonization. The thin atmosphere is composed mostly of carbon dioxide, with traces of nitrogen and argon. This composition affects everything from weather patterns to potential human habitation. Surface temperatures on Mars vary widely, typically ranging from -125 degrees Celsius at the poles to up to 20 degrees Celsius near the equator during the day. These extreme temperature fluctuations can pose significant challenges for human survival. Understanding these variations is crucial for designing habitats and life support systems. Mars experiences seasons similar to Earth due to its axial tilt. However, its seasons are almost twice as long because a Martian year is about 687 Earth days. This seasonal variation impacts atmospheric pressure and temperature, influencing weather patterns. Dust storms are a common feature on Mars, ranging from small dust devils to planet-wide events. These storms can last for days or even months, reducing sunlight and affecting solar-powered equipment. Studying these storms helps in developing strategies to mitigate their impact on human missions. The Martian atmosphere is too thin to support human breathing, with a surface pressure less than 1% of Earth's. This low pressure also means liquid water cannot exist on the surface for long periods. Advanced life support systems will be necessary to provide breathable air and manage pressure differences. Water vapor exists in the Martian atmosphere, but in very small amounts. Seasonal changes can cause this vapor to condense and form frost or thin clouds. Understanding these cycles is important for managing water resources for a human colony. Mars has polar ice caps made primarily of water ice, with seasonal layers of carbon dioxide ice. These ice caps expand and contract with the seasons, influencing atmospheric pressure. They are also potential sources of water for future colonists. The thin atmosphere means Mars lacks a significant greenhouse effect, resulting in colder temperatures. However, certain areas exhibit localized warming due to geological activity. Exploring these areas could provide insights into natural heat sources for human use. Mars's low atmospheric density provides little protection from solar and cosmic radiation. This exposure is a major concern for human health and requires robust shielding solutions. Understanding radiation levels across the planet helps in selecting safer locations for habitation. The presence of methane in the Martian atmosphere has intrigued scientists, suggesting possible biological or geological sources. Methane levels vary with the seasons, indicating active processes on the planet. Investigating these sources could provide clues about potential past or present life. Wind patterns on Mars are influenced by the planet's rotation, topography, and atmospheric composition. These winds can shape the landscape and affect surface operations. Studying wind behavior helps in designing structures and planning surface activities. Mars' lower gravity, about 38% of Earth's, affects atmospheric retention and weather patterns. This reduced gravity also impacts human physiology and the design of equipment. Understanding these effects is vital for long-term colonization efforts. The lack of a global magnetic field allows solar wind to strip away the Martian atmosphere. This process has contributed to the thin atmosphere observed today. Researching this interaction helps us understand atmospheric loss and its implications for future terraforming efforts. Seasonal variations in atmospheric pressure are driven by the sublimation and deposition of carbon dioxide from the polar ice caps. This cycle affects weather patterns and potential human activities. Monitoring these changes helps in planning for seasonal shifts. Finally, studying the climate and atmosphere of Mars provides valuable data for comparative planetology. Insights gained from Mars can inform our understanding of other planets, including Earth. This knowledge enhances our overall grasp of planetary science and the potential for life beyond Earth. Water is a crucial resource for sustaining human life on Mars, and its presence on the planet is a key focus of exploration. Evidence of water on Mars comes from various sources, including polar ice caps, subsurface ice, and ancient river valleys. These findings suggest that Mars once had a much wetter climate. The polar ice caps on Mars contain vast amounts of water ice, particularly in the northern cap. During the Martian summer, some of this ice sublimates into the atmosphere, contributing to seasonal changes. These ice caps are essential for understanding the planet's water cycle. Subsurface ice deposits have been detected across many regions of Mars, especially in the mid-latitudes. Radar data from orbiting spacecraft have revealed these hidden reserves. Accessing this ice will be critical for future human missions. Ancient river valleys and outflow channels provide strong evidence of liquid water flowing on Mars' surface in the past. These features indicate that Mars had a more temperate climate billions of years ago. Studying these areas helps us understand the planet's hydrological history. Recent discoveries suggest that liquid water might still exist on Mars today, albeit in very small amounts. Salty brines could allow water to remain liquid at lower temperatures. This potential for liquid water is a key consideration for future exploration and colonization. Water ice has also been found mixed with the Martian soil or regolith. This ice-rich regolith could be a valuable resource for future settlers. Extracting water from the soil will be a vital part of sustaining a human presence on Mars. The search for underground aquifers is ongoing, as these could provide more accessible water sources. Radar and other remote sensing technologies are crucial in this effort. Finding liquid water underground would be a major breakthrough for Mars colonization. The presence of hydrated minerals, such as clays and sulfates, indicates that water was once abundant on Mars. These minerals form in the presence of water, offering further evidence of the planet's wet past. Analyzing these minerals helps reconstruct Mars's climatic history. Glaciers on Mars, particularly in the mid-latitudes, contain large amounts of water ice. These glaciers are remnants of a more ice-rich past and can provide insights into the planet's climate cycles. They are also potential water sources for future missions. Mars' atmosphere contains trace amounts of water vapor, which varies seasonally. Understanding this water vapor cycle is important for managing water resources. It also helps in studying the planet's overall climate system. Technologies for extracting water on Mars are being developed, including methods to mine ice and extract water from the soil. These technologies are crucial for supporting human life and agriculture on Mars. Effective water extraction will be a cornerstone of Martian colonization. Using water from Mars reduces the need to transport it from Earth, significantly lowering mission costs. In-situ resource utilization, or ISRU, is a key strategy for sustainable colonization. Developing efficient ISRU techniques is a primary goal for space agencies. Water on Mars can be used not only for drinking and irrigation, but also for producing oxygen and hydrogen through electrolysis. These elements are essential for breathable air and rocket fuel. Mastering this process is critical for long-term human presence on Mars. The potential for liquid water also raises the question of past or present life on Mars. If life ever existed on Mars, it would likely have depended on water. Discovering signs of life would be one of the most profound scientific discoveries. Finally, the presence of water resources on Mars transforms our approach to exploration and colonization. It opens up possibilities for creating a self-sustaining human colony. Understanding and utilizing Mars's water resources is essential for turning the dream of living on another planet into reality. Comparing Mars with Earth highlights both the challenges and opportunities for colonization. Mars is about half the size of Earth, with a diameter of roughly 6,800 kilometers. Its surface area is similar to the total land area of Earth, offering ample space for exploration and settlement. Mars has a day length very close to that of Earth, with a Martian day, or sol, lasting about 24.6 hours. This similarity makes it easier for humans to adapt to the Martian day-night cycle. However, a Martian year is nearly twice as long as an Earth year, impacting seasonal activities. The gravitational pull on Mars is about 38% that of Earth. This lower gravity affects everything from human physiology to the design of structures and equipment. Understanding and adapting to Mars' gravity is crucial for long-term habitation. Mars's atmosphere is much thinner than Earth's, with surface pressure less than 1% of what we experience here. This thin atmosphere means that liquid water cannot remain stable on the surface. Advanced life support systems are necessary to create breathable air and manage pressure. The composition of Mars's atmosphere is vastly different, consisting mostly of carbon dioxide, with only trace amounts of oxygen. On Earth, our atmosphere is rich in nitrogen and oxygen, essential for human life. Colonists will need technologies to convert Martian CO2 into usable oxygen. Surface temperatures on Mars are much colder than on Earth, typically ranging from -125 degrees Celsius at the poles to up to 20 degrees Celsius near the equator. These extreme temperatures present significant challenges for maintaining habitable environments. Insulation and heating solutions are critical for survival. Mars lacks a global magnetic field unlike Earth, which means it has little protection from solar and cosmic radiation. This exposure poses serious health risks for humans. Effective radiation shielding is essential for safe habitation. While both planets have polar ice caps, Mars's caps are composed of both water ice and dry ice, or frozen carbon dioxide. These caps grow and shrink with the seasons, influencing atmospheric pressure. Understanding these dynamics is important for resource management. The surface of Mars is covered with dust and sand, creating a landscape shaped by wind-driven processes. On Earth, weathering and erosion are dominated by water and biological activity. Martian dust storms can be massive and long-lasting, impacting solar power and surface operations. Mars has a much lower atmospheric density than Earth, affecting aerodynamics and flight. This thin air makes traditional aircraft ineffective. Engineers are developing specialized drones and landers to operate in this environment. The red color of Mars is due to iron oxide or rust on its surface, giving it the nickname the Red Planet. In contrast, Earth's surface is diverse, with vast oceans, green forests, and varied landscapes. This visual difference underscores the unique environment of Mars. Mars's lack of liquid surface water contrasts sharply with Earth's abundant lakes, rivers, and oceans. This scarcity of liquid water on Mars is a major challenge for sustaining life. Finding and utilizing water resources on Mars is a top priority. Mars has a diverse topography with the tallest volcano and deepest canyon in the solar system. Earth's topography is equally varied, but shaped significantly by water and tectonic activity. The geological features of Mars provide both challenges and opportunities for exploration. The absence of active plate tectonics on Mars contrasts with Earth's dynamic crust. Earth's tectonic activity drives the formation of mountains, earthquakes, and volcanic eruptions. Mars' more static crust influences its geological and atmospheric evolution. Both planets share similarities in their axial tilt, resulting in seasons. However, Mars's longer orbit means its seasons are nearly twice as long as those on Earth. This extended seasonal cycle affects planning for agriculture and human activities on Mars. The potential for supporting life on Mars is a subject of intense scientific interest. The presence of water ice and possible subsurface liquid water are key factors. These water sources could support microbial life or future human settlers. Mars's past climate, which may have been warmer and wetter, suggests it could have supported life. Ancient river valleys and lake beds indicate that liquid water was once abundant. Understanding this past environment helps in assessing the potential for life. Current conditions on Mars are harsh, with low temperatures and high radiation levels. Despite this, extremophils on Earth thrive in similar conditions. These hardy organisms provide clues about the types of life that might survive on Mars. The discovery of methane in the Martian atmosphere hints at possible biological activity. Methane can be produced by both geological and biological processes. Identifying its source is crucial for understanding Mars's potential for life. Mars soil contains perchlorates, which can be used as a food source by certain microbes. These chemicals present both opportunities and challenges for life. Research into how organisms interact with perchlorates could reveal survival strategies. The subsurface of Mars is considered one of the best places to search for life. Shielded from harsh surface conditions, it might harbor liquid water. Drilling and exploring underground are essential for finding potential biospheres. Hydrothermal vents on Earth support diverse ecosystems, and similar features might exist on Mars. If Mars has or had hydrothermal activity, it could provide environments conducive to life. Investigating these areas is a high priority for astrobiologists. The presence of organic molecules on Mars, detected by rovers, suggests potential building blocks of life. These molecules are fundamental to biological processes. Their origin and distribution help assess Mars's habitability. Mars's thin atmosphere poses challenges for life, but it also means fewer weather disruptions. This stability could benefit certain types of life forms. Understanding atmospheric dynamics aids in predicting potential habitats. Seasonal changes on Mars, such as temperature and pressure fluctuations, impact potential life. Organisms would need to adapt to these cycles. Studying these adaptations provides insights into life's resilience. Radiation levels on Mars are high due to the lack of a magnetic field and thick atmosphere. Life forms would need to cope with or avoid this radiation. Research into radiation-resistant organisms guides the search for Martian life. The discovery of briny water on Mars raises the possibility of habitable niches. Salts lower the freezing point of water, allowing it to remain liquid in cold conditions. These brines could be habitats for microbial life. If life exists on Mars, it likely uses different biochemistry than Earth life. Understanding potential Martian biochemistry expands the scope of astrobiology. This knowledge helps in designing better life detection experiments. Photosynthetic life would struggle on Mars due to low light levels and high UV radiation. However, chemotrophic life could thrive using chemical energy sources. Exploring these possibilities broadens our search criteria. Finding life on Mars would have profound implications for understanding life's universality. It would suggest that life can arise independently in diverse environments. This discovery would redefine our place in the universe. Spacecraft and transportation are critical components of Mars colonization. The journey to Mars requires advanced spacecraft capable of carrying humans and supplies. Developing these technologies is a major focus for space agencies. The first step in Mars transportation is launching from Earth. Powerful rockets like the Space Launch System and Falcon Heavy are designed for this task. These rockets must carry payloads into orbit and beyond. Once in space, spacecraft need to travel the vast distance to Mars. This journey takes about 6 to 9 months, depending on orbital alignments. Efficient propulsion systems are essential for this long-duration flight. Current propulsion technologies include chemical rockets and ion thrusters. Chemical rockets provide high thrust but require significant fuel. Ion thrusters are more efficient but provide lower thrust. Future propulsion concepts, such as nuclear thermal and electric propulsion, offer potential benefits. These technologies could shorten travel time and reduce fuel requirements. Research and development are ongoing in these areas. Spacecraft must also provide life support for the crew during the journey. This includes air, water, food, and waste management systems. Ensuring the health and safety of astronauts is a top priority. Radiation protection is another critical aspect of spacecraft design. Spacecraft need shielding to protect the crew from cosmic rays and solar radiation. Various materials and design strategies are being explored. Landing on Mars presents unique challenges due to its thin atmosphere. Traditional parachutes are less effective, so alternative methods are needed. Powered descent and inflatable decelerators are among the solutions being tested. Surface mobility is essential for exploring and settling Mars. Rovers like Curiosity and Perseverance have paved the way for future missions. Human-rated rovers will need to be larger and more capable. Transporting cargo to Mars requires specialized vehicles. These vehicles must carry equipment, habitats, and supplies. Efficient cargo transport is vital for building and sustaining a colony. Mars rovers will need to navigate diverse terrain, from rocky surfaces to sandy dunes. Advanced navigation systems and autonomous capabilities are crucial. These technologies will enable rovers to operate independently. Energy sources for transportation on Mars include solar power and nuclear reactors. Solar power is abundant but variable, while nuclear reactors provide consistent energy. Choosing the right energy mix is important for long-term operations. Building infrastructure on Mars will involve various transport methods. This includes aerial drones, surface vehicles, and possibly even rail systems. Each method has its advantages and challenges. Communication between Earth and Mars is essential for coordination and support. Delays in communication due to the distance can be significant. Developing robust and reliable communication networks is a priority. The development of spacecraft and transportation systems is a collaborative effort. Space agencies, private companies, and international partners are all contributing. This collaboration is key to overcoming the challenges of Mars colonization. Life support systems are crucial for sustaining human life on Mars. These systems provide air, water, food, and waste management. Developing reliable and efficient life support is essential for long-term missions. Air supply is a fundamental component. On Mars, we need to produce oxygen from available resources. Technologies like the MOXIE experiment on Perseverance are testing oxygen generation from carbon dioxide. Water recycling is vital for survival. Systems that reclaim water from waste and condensation are being developed. Efficient water management reduces the need for resupply from Earth. Food production on Mars will rely on both pre-packaged supplies and local cultivation. Hydroponics and other soil-free growing methods are being researched. Growing food locally supports sustainability and self-sufficiency. Waste management includes processing human waste and recycling materials. These systems must operate efficiently to prevent contamination. Proper waste management is key to maintaining a healthy living environment. Temperature control is another critical aspect. Mars has extreme temperature variations that habitats must withstand. Insulation and heating systems ensure a stable internal climate. Radiation protection is essential due to Mars' lack of a magnetic field. Habitats need shielding to protect inhabitants from harmful radiation. Using local materials for shielding is a potential solution. Life support systems must also provide adequate lighting and ventilation. Proper air circulation prevents the buildup of harmful gases. Artificial lighting supports plant growth and human circadian rhythms. Monitoring systems are necessary to track the performance of life support components. Sensors and automated controls help maintain optimal conditions. These systems ensure the safety and well-being of the crew. Emergency protocols are critical for dealing with system failures. Redundant systems and fail-safes provide backup in case of malfunction. Preparedness for emergencies is crucial for mission success. Power supply is fundamental to life support operations. Solar panels and nuclear reactors are primary energy sources. Reliable power ensures continuous operation of life support systems. Habitat design integrates life support systems into the living space. Modular designs allow for expansion and adaptation. Efficient layout and space utilization enhance livability. Transportable life support systems are needed for exploration missions. Portable units support astronauts during excursions away from the main habitat. These systems provide essential resources for mobility. Life support systems must be tested extensively before deployment. Simulations and trials on Earth help refine these technologies. Ensuring reliability and functionality is paramount. Collaboration between space agencies and private companies drives innovation. Sharing knowledge and resources accelerates development. This teamwork is vital for advancing life support technologies. Habitat construction on Mars requires innovative engineering solutions. The habitats must protect inhabitants from extreme temperatures, radiation, and dust storms. Designing these shelters is a top priority for ensuring safety and comfort. Materials for construction can be sourced from both Earth and Mars. Using Martian regolith to create bricks or concrete reduces the need for transporting materials. This approach supports sustainable building practices. 3D printing technology is pivotal for constructing habitats. It allows for rapid and precise building of complex structures. This method also enables the use of local materials, minimizing supply needs. Inflatable habitats offer a flexible solution for initial settlement. These structures can be compact during transport and expanded on Mars. They provide a quick and efficient way to establish a living space. Underground habitats provide natural protection from radiation and temperature fluctuations. Digging into the Martian surface creates insulated and secure living areas. This approach leverages the natural geology for enhanced safety. Solar panels integrated into habitat designs can provide a reliable energy source. These panels convert sunlight into electricity, supporting various systems. Efficient energy management is crucial for maintaining operations. Radiation shielding is essential in habitat construction. Materials like polyethylene or regolith can block harmful rays. Effective shielding ensures the long-term health of residents. Habitat designs must include robust airlock systems. These airlocks prevent contamination and maintain internal pressure. Secure entry and exit points are vital for daily operations. Water and waste management systems need to be integrated into the habitat. Recycling water and processing waste are critical for sustainability. These systems support a closed-loop environment. Life support systems are central to habitat functionality. These systems regulate air, water, and temperature. Ensuring their reliability is key to the success of the habitat. Communication systems within the habitat enable coordination and safety. Reliable links to Earth and within the Martian colony are necessary. These systems ensure connectivity for operations and emergencies. Storage solutions for food, equipment, and supplies must be considered. Efficient use of space and organization supports daily living. Proper storage ensures accessibility and conservation of resources. Modular habitat designs allow for expansion as the colony grows. Connecting multiple units creates a larger, adaptable living space. This flexibility supports long-term development plans. Recreational and social areas are important for mental health. Designing spaces for relaxation and interaction fosters community. These areas enhance the overall quality of life. Testing and prototyping habitats on Earth are essential steps. Simulated Mars environments help refine designs and systems. Ensuring readiness before deployment is critical for success. Communication systems are vital for connecting Mars colonists with Earth and each other. Reliable communication ensures coordination, safety, and support. Developing robust networks is essential for mission success. The distance between Mars and Earth creates significant communication delays. Signals take between 4 to 24 minutes to travel one way. This delay requires careful planning and autonomous systems. Satellite networks around Mars can facilitate constant communication. These satellites relay signals between the surface and Earth. Establishing a reliable satellite constellation is a priority. Surface communication systems link habitats, rovers, and astronauts. These networks use radio frequencies for local communication. Ensuring strong and clear signals is crucial for daily operations. High-gain antennas are used to transmit data over long distances. These antennas can focus signals to reach Earth efficiently. Proper alignment and maintenance are key to their effectiveness. Laser communication offers higher data rates compared to radio. This technology can transmit large amounts of data quickly. Implementing laser systems could revolutionize space communication. Communication hubs on Mars can manage data flow and distribution. These hubs ensure that all messages and data are routed correctly. Centralized control supports organized and efficient communication. Redundancy in communication systems is critical for reliability. Backup systems ensure continuous operation in case of failures. This redundancy is crucial for safety and mission success. Power supply for communication equipment must be consistent. Solar panels and batteries can provide necessary energy. Ensuring uninterrupted power supports continuous communication. Emergency communication protocols are essential. These protocols guide responses to crises and system failures. Effective emergency plans enhance safety and preparedness. Data encryption protects communication from interception. Secure channels are necessary to safeguard sensitive information. Implementing strong encryption ensures privacy and security. Software updates for communication systems must be managed carefully. Regular updates maintain functionality and security. Remote update capabilities are important for long-term missions. Collaborative tools enable teamwork between Mars and Earth. Video conferencing, file sharing, and real-time data access support collaboration. These tools bridge the distance between the two planets. Testing communication systems on Earth ensures they work on Mars. Simulations and trials identify potential issues and solutions. Ensuring readiness before deployment is crucial for effectiveness. International cooperation enhances communication infrastructure. Sharing technology and resources builds a robust network. Collaboration ensures comprehensive and reliable communication systems. Physical health challenges on Mars are significant due to the planet's harsh environment. The low gravity, which is only 38% of Earth's, affects muscle and bone density. Prolonged exposure can lead to muscle atrophy and bone loss, necessitating rigorous exercise regimens. Radiation exposure is another major concern on Mars. Without a magnetic field and thick atmosphere, the surface is bombarded by cosmic rays and solar radiation. Long-term exposure increases the risk of cancer and other health issues, making effective shielding essential. The cold temperatures on Mars pose additional health risks. Average temperatures can plummet to -80 degrees Fahrenheit. Proper insulation and heating systems are crucial to prevent hypothermia and frostbite. The thin atmosphere means there's very little oxygen available. Life support systems must provide a continuous supply of breathable air. Hypoxia, or oxygen deficiency, can occur quickly without these systems. Dust storms on Mars can last for weeks and cover the entire planet. The fine dust particles can infiltrate habitats and equipment. Inhalation of Martian dust poses respiratory risks and can damage electronic systems. The isolation and confinement of living on Mars impact mental health. Limited social interactions and the inability to return to Earth can lead to psychological stress. Regular mental health support and recreational activities are vital. Nutrition is a key component of physical health. Growing food on Mars using hydroponics and other methods is necessary to provide a balanced diet. Deficiencies in vitamins and minerals must be monitored and corrected. Microgravity affects cardiovascular health. Astronauts on the International Space Station experience changes in heart function and blood flow. Similar effects are expected on Mars, requiring ongoing health monitoring. Fluid distribution in the body changes in low gravity. This can lead to increased intracranial pressure and vision problems. Countermeasures are needed to manage these physiological changes. The immune system may weaken over time in a Martian environment. Reduced gravity and radiation exposure can impact immune response. Ensuring a sterile environment and monitoring health are critical. Physical injuries must be treated promptly on Mars. Medical facilities need to be equipped to handle emergencies and surgeries. Training for all crew members in basic medical procedures is essential. Exercise is crucial to counteract the effects of low gravity. Resistance and cardiovascular training help maintain muscle and bone strength. Dedicated exercise areas and equipment are necessary in habitats. The duration of Mars missions means long-term health effects need consideration. Chronic conditions such as osteoporosis or vision impairment may develop. Ongoing medical research and support are necessary. Hydration is important in the dry Martian environment. Adequate water supply and monitoring are required to prevent dehydration. Water recycling systems play a key role in sustaining hydration. Continuous health monitoring systems are essential for early detection of issues. Wearable technology and regular checkups help track health status. These systems ensure prompt intervention when needed. Psychological effects of living on Mars are profound and multifaceted. The isolation from Earth and the small size of the crew can lead to feelings of loneliness. Limited social interaction increases the risk of depression and anxiety. The confined living spaces on Mars habitats can cause cabin fever. Lack of privacy and personal space may lead to stress and interpersonal conflicts. Designing habitats to include private areas can help mitigate this issue. The constant awareness of being in a hostile environment can cause chronic stress. Mars' inhospitable climate and potential dangers require constant vigilance. Stress management techniques and mental health support are crucial. The long duration of Mars missions can exacerbate psychological strain. Being away from family and friends for extended periods is challenging. Regular communication with loved ones and psychological counseling are important. Monotony and lack of variety in daily activities can lead to boredom and demotivation. Engaging in hobbies, recreational activities, and varied tasks helps maintain morale. Ensuring a diverse routine is key to mental well-being. The lack of natural light on Mars can disrupt circadian rhythms. This disruption can affect sleep patterns and overall health. Artificial lighting that mimics Earth's day-night cycle can help regulate sleep. The potential for emergencies and the need for self-reliance can induce anxiety. Training and preparedness are essential to build confidence and reduce fear. Knowing how to handle crises helps alleviate anxiety. The pressure to succeed on a high-stakes mission can lead to performance anxiety. Crew members may feel the weight of expectations from Earth. Supportive leadership and a collaborative environment can ease this pressure. The perception of time can be altered on Mars due to the length of missions. Long-term goals may seem daunting and affect motivation. Setting short-term achievable goals helps maintain focus and a sense of accomplishment. Cultural and individual differences among crew members can lead to misunderstandings. Effective communication and conflict resolution skills are vital. Fostering a culture of respect and understanding is essential for harmony. The lack of nature and outdoor environments can affect mental health. Green spaces and access to nature are important for psychological well-being. Indoor plants and virtual reality nature experiences can provide relief. The constant presence of technology and screens can lead to digital fatigue. Balancing screen time with offline activities is important. Encouraging physical activity and relaxation helps counteract this fatigue. The anticipation of returning to Earth can create both excitement and anxiety. Readaptation to Earth's environment and society can be challenging. Preparing for re-entry and reintegration is part of the psychological support. Team dynamics play a crucial role in psychological well-being. Strong, supportive relationships within the crew are essential. Team-building activities and trust exercises help build cohesion. The overarching sense of purpose and mission can positively influence mental health. Contributing to a historic endeavor provides a sense of meaning. Maintaining a clear vision of the mission's goals helps sustain motivation and morale. Radiation protection is a critical concern for Mars colonists. Without a magnetic field and thick atmosphere, Mars exposes inhabitants to harmful cosmic rays and solar radiation. Effective shielding is essential to ensure long-term health and safety. One method of radiation protection is using the Martian regolith. Thick layers of this soil can be used to build protective barriers. Regolith can absorb and block significant amounts of radiation. Water is another effective radiation shield. Storing water in walls and ceilings of habitats can provide an additional layer of protection. This dual-purpose use helps conserve space and resources. Habitat design can also incorporate radiation-resistant materials. Advanced composites and polymers offer high radiation resistance. These materials are integrated into the structural design of living spaces. Subsurface habitats offer natural radiation protection. Building underground or within Martian caves can significantly reduce exposure. These locations utilize the planet's geology to shield inhabitants. Spacesuits must be designed to protect against radiation. Enhanced suits with built-in shielding allow for safer exploration. Ensuring suits are both protective and functional is a key engineering challenge. Portable radiation shelters provide emergency protection. These shelters can be deployed quickly during solar storms. Having these ready-to-use structures is crucial for mission safety. Radiation monitoring systems are essential for real-time safety. Sensors placed in habitats and suits track exposure levels. These systems alert colonists to dangerous radiation spikes. Research into pharmaceutical countermeasures is ongoing. Certain medications can help mitigate radiation's biological effects. Developing effective drugs is a focus of current medical research. Regular health monitoring can detect early signs of radiation exposure. Medical checkups and diagnostic tools help manage long-term risks. Preventative care is vital for maintaining health on Mars. Radiation protection strategies must be continually updated. Advances in technology and new research findings drive improvements. Staying ahead of potential risks ensures ongoing safety. Collaborative efforts enhance radiation protection solutions. Sharing data and techniques between space agencies accelerates progress. International cooperation is key to tackling this global challenge. Public education on radiation risks and protection measures is important. Understanding the science helps garner support for space exploration. Clear communication fosters public trust and interest. Long-term solutions may involve terraforming efforts. Creating a thicker atmosphere or magnetic field could reduce radiation. These ambitious projects represent the future of planetary protection. Continued innovation in radiation protection is essential for Mars colonization. Investing in research and technology paves the way for safe, sustainable living. Overcoming radiation challenges is crucial for the success of human missions to Mars. Medical facilities on Mars are essential for the health and safety of colonists. These facilities must be equipped to handle emergencies, routine care, and long-term health monitoring. Advanced medical technology and telemedicine support are critical components. A well-equipped infirmary is the cornerstone of any Martian habitat. It needs to include diagnostic equipment, surgical tools, and life support systems. These facilities must be prepared for a wide range of medical scenarios. Telemedicine allows for remote consultations with specialists on Earth. High-quality communication systems enable real-time diagnostics and treatment advice. This connection is vital for dealing with complex medical issues. Robotic surgery units can perform precise operations with remote assistance. These units reduce the need for specialist surgeons on Mars. Robotic systems enhance surgical capabilities in a low-gravity environment. Medical research on Mars focuses on understanding the effects of prolonged space travel. Studying changes in muscle, bone density, and cardiovascular health is a priority. This research informs better health protocols for astronauts. Isolation can impact mental health, making psychological support crucial. Medical facilities must include mental health resources and spaces for counseling. Addressing mental health proactively is key to a healthy colony. Pharmaceutical supplies must be carefully managed and replenished. The production of certain medications on Mars could be explored. Ensuring a steady supply chain is critical for ongoing healthcare. Emergency response protocols are essential for life-threatening situations. Medical staff must be trained in advanced emergency procedures. Quick and efficient responses can save lives. Medical research also explores the impact of Martian gravity on human physiology. Understanding how reduced gravity affects the body helps develop countermeasures. This research is vital for long-term colonization efforts. Dental care cannot be overlooked in the harsh environment of Mars. Facilities must include dental equipment for routine checkups and emergency procedures. Oral health is an important aspect of overall well-being. Radiation exposure necessitates ongoing health monitoring and research. Developing effective treatments for radiation sickness is a high priority. This research contributes to safer long-term habitation. Preventative care and routine health checkups are essential for early detection of issues. Regular screenings help maintain the overall health of the colony. Early intervention can prevent minor issues from becoming major problems. Medical training for all crew members enhances overall safety. Basic medical skills enable immediate response to health issues. Comprehensive training programs are necessary for preparedness. Collaborative research with Earth-based institutions enhances medical knowledge. Sharing data and findings accelerates medical advancements. International cooperation is key to addressing health challenges on Mars. Investing in medical infrastructure and research ensures the longevity of Mars colonies. Advanced medical care supports the well-being of all inhabitants. Continuous improvement in medical technology is essential for sustainable living on Mars. Long-term living conditions on Mars require careful planning and adaptation. The Martian environment presents unique challenges that must be addressed for sustained habitation. Ensuring comfort and safety is essential for the well-being of colonists. Habitat durability is a primary concern. Structures must withstand Mars's extreme temperatures, dust storms, and radiation. Robust construction materials and designs are crucial for longevity. Sustainable food production is vital for long-term survival. Hydroponic and aeroponic systems can grow crops without soil. Developing efficient agricultural practices ensures a steady food supply. Water recycling systems must be highly efficient. Reclaiming water from waste and condensation minimizes the need for resupply. Advanced filtration and purification technologies are essential. Energy independence is key for maintaining living conditions. Solar panels and nuclear reactors can provide reliable power. Ensuring consistent energy availability supports all other systems. Maintaining a stable indoor climate is critical. Temperature control systems must keep habitats warm in the cold Martian environment. Effective insulation and heating are necessary for comfort. Psychological well-being is as important as physical health. Providing spaces for relaxation and social activities helps reduce stress. Designing habitats to support mental health is essential. Long-term exposure to low gravity affects the body. Regular exercise is needed to counteract muscle and bone loss. Specialized workout equipment and routines are necessary. Radiation protection strategies must be continually improved. Shielding habitats and providing protective suits are ongoing priorities. Research into new materials and technologies is vital. Developing a sense of community enhances living conditions. Shared goals and cooperative tasks build strong social bonds. Fostering a positive, collaborative environment is crucial. Adaptation to the Martian day-night cycle supports health. Artificial lighting systems should mimic Earth's natural light patterns. This helps regulate sleep and circadian rhythms. Educational and recreational activities are important for quality of life. Providing opportunities for learning and entertainment keeps colonists engaged. These activities support overall well-being. Efficient waste management maintains a clean living environment. Recycling and repurposing materials reduce waste. Advanced waste processing technologies are essential. Communication with Earth helps reduce feelings of isolation. Regular contact with family and friends supports mental health. Robust communication systems ensure connectivity. Long-term living requires robust infrastructure maintenance. Regular checks and repairs keep systems running smoothly. Preventative maintenance is key to avoiding major issues. Continuous innovation and adaptation ensure long-term success. Learning from experiences and improving technologies is a constant process. Commitment to progress supports sustainable living on Mars. In-situ resource utilization, or ISRU, is critical for sustainable Mars colonization. ISRU involves using local resources to support human life and operations. This approach reduces the need for costly supply missions from Earth. Water extraction from Martian ice is a key ISRU process. Ice can be melted and purified for drinking and other uses. Water is also vital for producing oxygen and hydrogen through electrolysis. Mars's atmosphere, rich in carbon dioxide, can be converted into oxygen. Technologies like the MOXIE experiment demonstrate this capability. Producing breathable air on Mars is essential for long-term habitation. Local materials can be used for construction. Regolith can be processed into bricks or concrete for building habitats. This reduces the need to transport building materials from Earth. ISRU can also provide fuel for return missions. Methane and oxygen can be produced from water and carbon dioxide. Creating fuel on Mars supports mission sustainability and flexibility. Soil and regolith can be used to grow plants. Hydroponics and other soil-free methods benefit from local materials. Cultivating crops locally supports food security for colonists. Extracting useful minerals from Martian soil is another ISRU focus. Metals and other elements can be used for manufacturing and repairs. Efficient mining techniques are being developed for this purpose. ISRU reduces reliance on Earth and lowers mission costs. By utilizing local resources, missions become more self-sufficient. This approach supports long-term colonization and exploration. Energy production can benefit from ISRU. Local materials can be used to build and maintain solar panels. This supports a sustainable energy infrastructure on Mars. ISRU technologies must be robust and reliable. They need to operate in Mars's harsh environment with minimal maintenance. Ensuring their efficiency and durability is a primary goal. Ongoing research and testing are essential for advancing ISRU. Simulations and field tests help refine these technologies. Continuous improvement ensures their effectiveness for future missions. International cooperation accelerates ISRU development. Sharing knowledge and resources enhances technological progress. Collaborative efforts are key to overcoming ISRU challenges. ISRU also includes waste recycling and management. Converting waste into useful products supports sustainability. Effective waste processing is vital for maintaining a clean environment. Implementing ISRU strategies requires careful planning. Integration with other systems is necessary for overall mission success. Coordinated efforts ensure that ISRU meets the colony's needs. The success of ISRU will shape the future of Mars colonization. Developing these technologies is critical for establishing a self-sufficient human presence. Commitment to ISRU innovation supports the long-term vision of living on Mars. Mining and material extraction on Mars are crucial for building a self-sustaining colony. Utilizing Martian resources reduces dependency on supplies from Earth. Efficient extraction methods are essential for long-term success. Regolith, the loose soil and rock on Mars's surface, is a valuable resource. It can be processed into building materials like bricks and concrete. These materials are vital for constructing habitats and infrastructure. Ice mining provides essential water for drinking, agriculture, and oxygen production. Techniques for locating and extracting ice are being developed. Access to water is a cornerstone of Mars colonization. Mars is rich in various minerals including iron, aluminum, and magnesium. These metals can be used for manufacturing tools, equipment, and structures. Mining operations must be efficient and sustainable. Robotic mining equipment will play a key role on Mars. Robots can operate in harsh conditions and perform repetitive tasks. Automation increases efficiency and reduces the need for human labor. Advanced drilling techniques are necessary to access subsurface resources. These techniques must be adapted to Mars's unique geology. Effective drilling is crucial for reaching water, ice, and mineral deposits. Processing regolith to extract useful elements involves various technologies. Electrolysis can separate metals from their ores. These processes need to be efficient and environmentally friendly. 3D printing using locally sourced materials can revolutionize construction. This technology allows for on-demand manufacturing of parts and tools. It supports flexibility and reduces the need for spare parts from Earth. Energy is required for mining and material processing. Solar power and nuclear energy are primary sources on Mars. Ensuring a stable energy supply supports continuous operations. Waste management is an important aspect of mining activities. Recycling and reusing waste materials minimizes environmental impact. Sustainable practices are essential for long-term viability. Transporting materials across the Martian surface presents challenges. Efficient transportation systems are needed to move extracted resources. Rovers and automated vehicles will play a key role in logistics. Safety protocols are critical for mining operations. Ensuring the well-being of workers and the integrity of equipment is paramount. Robust safety measures prevent accidents and system failures. Collaboration with international partners enhances mining technology development. Sharing expertise and resources accelerates progress. Global cooperation is vital for overcoming technical challenges. Testing mining techniques on Earth provides valuable insights. Simulated Martian environments help refine methods and equipment. These tests ensure readiness for actual deployment on Mars. Continual innovation in mining and material extraction supports the growth of Mars colonies. Developing sustainable and efficient methods is crucial for self-sufficiency. This progress lays the foundation for a thriving human presence on Mars. Water extraction and usage are pivotal for sustaining life on Mars. Accessing water ice from beneath the surface is a primary goal. Techniques for identifying and mining this ice are being refined. Water can be extracted by melting subsurface ice deposits. This process requires drilling and heating technologies. Extracted water is then purified for consumption and use. Recycling water is essential for conserving resources. Systems that reclaim water from waste and condensation are vital. These systems ensure a continuous supply of clean water. Water is crucial for producing oxygen and hydrogen. Electrolysis can split water molecules into these elements. This process supports breathable air and rocket fuel production. Agriculture on Mars depends on a reliable water supply. Hydroponic systems use water to grow crops without soil. Efficient water usage maximizes crop yields and supports food security. Storing water for future use is important for stability. Large storage tanks or underground reservoirs can hold reserves. These reserves provide a buffer against shortages. Water usage must be carefully monitored and managed. Sensors and automated systems track consumption and detect leaks. Effective management ensures sustainable water use. Transporting water across the Martian surface requires robust infrastructure. Pipelines and transport vehicles move water to where it's needed. Ensuring efficient delivery supports all colony operations. Emergency water supplies are necessary for safety. Backup systems provide water in case of primary system failure. These supplies are critical for survival during crises. Research into water extraction technologies continues to evolve. New methods and innovations improve efficiency and sustainability. Ongoing research is essential for long-term success. Water is also used in construction and manufacturing. Mixing with regolith creates concrete for building habitats. This usage supports infrastructure development. Water's role in radiation shielding is another key aspect. Storing water in habitat walls provides protection from cosmic rays. This dual-purpose use enhances safety and resource efficiency. Collaboration with international partners advances water technology. Sharing knowledge and techniques accelerates progress. Global cooperation is vital for overcoming challenges. Testing water extraction methods on Earth simulates Martian conditions. These tests help refine technologies before deployment. Ensuring reliability is crucial for mission success. Efficient water extraction and usage lay the foundation for Mars colonization. Sustainable practices ensure a steady supply of this vital resource. Mastering water management is key to thriving on the red planet. Food production and agriculture are critical for sustaining a Mars colony. Growing food locally reduces dependence on Earth supplies. Developing effective agricultural systems is a priority. Hydroponics allows plants to grow without soil using nutrient-rich water. This method conserves water and supports crop growth in confined spaces. Hydroponic systems are ideal for the Martian environment. Aeroponics is another soil-free method, where plant roots are misted with nutrients. This technique uses even less water than hydroponics. Aeroponics is efficient and adaptable to various crops. Greenhouses provide controlled environments for plant growth. They can be equipped with artificial lighting and climate control. Greenhouses protect plants from harsh Martian conditions. Choosing the right crops is essential for a balanced diet. Leafy greens, tomatoes, and herbs are suitable for hydroponic and aeroponic systems. These crops grow quickly and provide essential nutrients. Supplementing diets with algae and fungi offers additional nutrition. Spirulina and mushrooms can grow in Martian habitats. These foods are rich in protein and vitamins. Efficient water management is vital for agriculture. Recycling water within the system conserves resources. Advanced filtration ensures water purity for plant growth. Lighting systems must support photosynthesis. LED lights can be tuned to optimal wavelengths for plant growth. Efficient lighting reduces energy consumption. Soil-based agriculture may also be explored. Martian regolith can be modified to support plant growth. Adding organic matter and nutrients creates fertile soil. Pollination is crucial for certain crops. Manual pollination or using pollinator robots can ensure plant reproduction. Ensuring successful pollination supports crop yields. Pest management is necessary to protect crops. Integrated pest management strategies minimize chemical use. Biological controls and monitoring systems keep pests in check. Genetic engineering can enhance crop resilience. Developing plants that thrive in Martian conditions increases food security. Genetic modifications may improve growth rates and nutrient content. Regular monitoring of plant health is essential. Sensors and automated systems track growth and detect issues. Early intervention ensures healthy crops. Research and development continue to improve agricultural practices. Ongoing studies optimize growth conditions and resource use. Continuous innovation supports sustainable food production. Successful food production is key to a thriving Mars colony. Efficient agriculture ensures a steady food supply and supports colonist health. Mastering these techniques is essential for long-term survival on Mars. Waste management and recycling are essential for a sustainable Mars colony. Efficient systems reduce resource consumption and environmental impact. Developing robust waste solutions is a priority. Organic waste can be composted to create nutrient-rich soil. This compost supports agricultural efforts by improving soil quality. Composting recycles valuable nutrients back into the ecosystem. Human waste must be treated and recycled safely. Advanced treatment systems can convert waste into usable resources. These systems ensure hygiene and support resource recovery. Plastic waste can be recycled into new materials. In-situ recycling reduces the need for raw materials from Earth. Efficient plastic recycling supports manufacturing and maintenance. Metal waste is another critical area for recycling. Metals can be melted down and reformed into new tools and structures. This process conserves valuable materials and supports construction efforts. Electronic waste requires specialized recycling methods. Recovering components and materials from old electronics reduces waste. Effective e-waste recycling supports technological sustainability. Water recycling is vital for conserving this precious resource. Grey water from sinks and showers can be filtered and reused. Advanced filtration systems ensure water safety and availability. Air quality must be maintained through effective recycling systems. Air scrubbers remove carbon dioxide and other contaminants, ensuring clean air supports colonist health and safety. Paper and cardboard waste can be recycled into new paper products. This process reduces the need for fresh paper supplies from Earth. Efficient paper recycling supports sustainable living. Clothing and fabric waste can be repurposed or recycled. Old clothing can be used as insulation or broken down into new fibers. This approach conserves materials and reduces waste. Energy recovery from waste is another important strategy. Organic waste can be processed into biofuel or biogas. These renewable energy sources support colony energy needs. Waste management systems must be integrated into daily operations. Regular collection and processing prevent waste buildup. Efficient waste handling supports a clean and organized habitat. Automation can enhance waste management efficiency. Robots and automated systems can sort and process waste. Automation reduces manual labor and improves recycling rates. Education and training are essential for effective waste management. Colonists must understand proper waste disposal and recycling practices. Informed residents contribute to a sustainable community. Continuous improvement in waste management technologies is necessary. Ongoing research and development drive innovation. Advanced systems ensure long-term sustainability for the Mars colony. Design and construction of habitats on Mars must address several challenges. The harsh environment requires robust and resilient structures. Innovative designs ensure safety and comfort for the inhabitants. Modular habitats allow for easy expansion and adaptation. These units can be connected to form larger living spaces. Modular designs offer flexibility for future growth. Inflatable habitats provide a quick and efficient setup. These structures are compact during transport and expand upon arrival. Inflatable habitats are reinforced to withstand the Martian conditions. 3D printing technology is revolutionizing habitat construction. Using local materials like regolith, habitats can be printed on site. This method reduces the need for transporting building materials from Earth. Radiation protection is a critical aspect of habitat design. Thick walls made of regolith or water can shield inhabitants from harmful rays. Ensuring effective radiation shielding is vital for long-term health. Underground habitats offer natural protection from environmental hazards. Digging into the Martian surface provides insulation and safety. Subsurface living spaces leverage Mars' natural geology. Energy efficiency is essential for maintaining a stable habitat environment. Solar panels and other renewable energy sources power the habitats. Efficient energy management systems support all habitat operations. Life support systems must be integrated into the habitat design. These systems regulate air, water, and temperature. Reliable life support is crucial for sustaining human life. Habitat interiors should be designed for comfort and functionality. Ergonomic furniture and efficient layouts enhance living conditions. Creating a home-like atmosphere supports mental well-being. Safety features are a top priority in habitat construction. Airlocks, fire suppression systems, and emergency protocols ensure safety. These features protect inhabitants from potential hazards. Communication systems within the habitat enable connectivity. Reliable communication with Earth and between modules is essential. These systems support coordination and emergency responses. Recycling and waste management systems are built into the habitats. Efficient handling of waste materials reduces environmental impact. Integrated recycling supports a sustainable living environment. Habitat construction also considers psychological needs. Spaces for recreation and social interaction improve quality of life. Designing for mental health is as important as physical safety. Testing habitat designs on Earth simulates Martian conditions. Prototypes undergo rigorous evaluation to ensure effectiveness. These tests refine designs before deployment on Mars. Collaboration with international partners enhances habitat development. Sharing knowledge and resources drives innovation. Joint efforts ensure the creation of the best possible living spaces. Inflatable habitats are one of the most versatile options for Mars. They can be transported compactly and then expanded upon arrival. These habitats provide immediate shelter and can be reinforced with additional materials for durability. Underground habitats offer natural protection from radiation and temperature extremes. Excavating into the Martian surface allows for stable, insulated living spaces. These habitats leverage the planet's geology for enhanced safety. Surface domes are designed to provide robust and expansive living areas. Made from transparent materials, they allow natural light while shielding from the environment. These domes can house entire communities under one structure. Hybrid habitats combine multiple design elements to maximize benefits. They might integrate inflatable sections with underground components. This approach offers flexibility and resilience in harsh conditions. 3D printed habitats utilize local regolith to construct durable buildings. These structures can be tailored to specific needs and expanded over time. On-site printing reduces reliance on materials from Earth. Semi-buried habitats are partially dug into the ground for added protection. The exposed sections are reinforced to withstand Mars conditions. This design balances the benefits of underground and surface living. Greenhouse habitats incorporate plant-growing areas within living spaces. They provide fresh air and food while enhancing mental well-being. Integrating agriculture directly into habitats supports sustainability. Mobile habitats can move across the Martian landscape. These units support exploration and temporary settlements. Mobility allows for flexibility in research and resource extraction. Clustered habitats create small communities of interconnected units. Each module serves a specific function like sleeping, dining, or research. This design supports communal living and resource sharing. Inflatable domes are a quick deploy option for immediate shelter. They expand to form large, open spaces for various uses. Reinforcement with local materials increases their longevity. Ice habitats utilize water ice as a primary building material. Ice provides excellent radiation shielding and insulation. These habitats are resource efficient and protective. Pressurized tents offer temporary and flexible living solutions. They are easy to deploy and transport, ideal for short-term missions. Pressurized tents ensure a stable atmosphere and quick setup. Composite habitats use advanced materials for enhanced durability. Combining different elements like carbon fiber and regolith creates robust structures. These habitats are designed for long-term use. Self-healing habitats incorporate materials that can repair damage autonomously. These advanced materials respond to wear and tear by restoring their integrity. Self-healing technology enhances the lifespan of habitats. Hollowed rock habitats utilize natural formations for shelter. Using existing caves or hollowing out rocks provides ready-made protection. This approach minimizes construction efforts and maximizes safety. Infrastructure for daily living on Mars is essential for a functional colony. Reliable power systems ensure continuous energy for all activities. Solar panels and nuclear reactors are primary sources. Water supply and sanitation systems must be efficient and sustainable. Recycling water from waste and condensation is critical. Advanced filtration ensures the safety and availability of water. Food production facilities are vital for a steady supply of fresh produce. Hydroponic and aeroponic systems support year-round farming. These facilities also include storage for preserved foods. Communication networks enable coordination and connectivity. Reliable links with Earth and within the colony are essential. These networks support daily operations and emergency responses. Transportation systems facilitate movement within and between habitats. Rovers and other vehicles are used for exploration and cargo transport. Efficient transport supports logistics and mobility. Healthcare facilities provide medical care and research capabilities. These include clinics, emergency rooms, and telemedicine links. Comprehensive healthcare ensures the well-being of all inhabitants. Educational infrastructure supports continuous learning and research. Classrooms, labs, and libraries cater to both children and adults. Ongoing education is crucial for personal and community development. Entertainment and recreational facilities enhance quality of life. Gyms, theaters, and social spaces offer relaxation and engagement. These areas support mental health and social interaction. Waste management systems ensure a clean and healthy environment. Recycling and composting reduce waste and support sustainability. Effective waste processing is essential for daily living. Safety and security infrastructure protect the colony from hazards. Fire suppression, airlocks, and surveillance systems are critical. These measures ensure the safety of people and property. Housing units are designed for comfort and functionality. They include sleeping areas, kitchens, and personal spaces. Well-designed housing supports daily life and personal well-being. Public spaces foster community interaction and cohesion. Parks, plazas, and communal dining areas encourage socializing. These spaces are integral to a vibrant community life. Maintenance facilities keep infrastructure operational. Workshops and storage areas support repairs and upkeep. Regular maintenance is crucial for the longevity of systems. Resource extraction and processing facilities support self-sufficiency. Mining, refining, and manufacturing are essential for local production. These facilities reduce dependence on Earth supplies. Administrative and governance structures manage daily operations. Offices and meeting rooms facilitate planning and decision-making. Effective governance ensures smooth functioning of the colony. Transport systems on Mars are essential for mobility and logistics. Rovers serve as the primary means of surface transportation. These vehicles are designed to navigate the rugged Martian terrain. Advanced rovers are equipped with autonomous navigation systems. These systems allow rovers to operate independently. Autonomous rovers increase efficiency and reduce the need for human intervention. Electric-powered rovers are preferred for their sustainability. Solar panels and rechargeable batteries provide energy. These power sources support long-distance travel. Cargo transport is crucial for moving supplies and equipment. Specialized rovers handle heavy loads and large items. Efficient cargo transport supports construction and maintenance. Aerial drones offer another mode of transportation. Drones can quickly survey large areas and deliver small packages. They provide flexibility for exploration and logistics. Maglev trains could be developed for long-distance travel. These trains use magnetic levitation to reduce friction. Maglev systems offer fast and efficient transport. Hyperloop systems are another potential option. These high-speed trains travel through low-pressure tubes. Hyperloop technology promises rapid transit across Mars. Surface vehicles must be robust and durable. They need to withstand dust, radiation, and temperature extremes. Designing resilient vehicles is a key challenge. Maintenance facilities are essential for transport systems. Workshops and repair stations keep vehicles operational. Regular maintenance ensures reliability and safety. Transport infrastructure includes roads and pathways. These routes connect habitats, work sites, and exploration areas. Well-planned infrastructure supports efficient travel. Charging stations are needed for electric vehicles. Solar-powered stations can be set up along travel routes. These stations ensure vehicles have access to energy. Transport hubs serve as central points for travel and logistics. Hubs include storage, maintenance, and coordination facilities. They streamline operations and support mobility. Safety protocols are critical for transport systems. Emergency procedures and safety equipment protect travelers. Ensuring safety is a top priority. Collaboration with Earth enhances transport technology. Sharing research and innovations drives progress. International cooperation supports the development of advanced systems. Testing transport systems on Earth simulates Martian conditions. These tests refine designs and improve functionality. Ensuring readiness before deployment is crucial. Expansion and scalability are crucial for a thriving Mars colony. Initial settlements must be designed with future growth in mind. Modular habitats and infrastructure allow for easy expansion. Scalable energy systems are vital for supporting a growing population. Solar farms and nuclear reactors can be expanded as needed. Ensuring a steady energy supply is essential for scalability. Agricultural systems must also be scalable. Hydroponic farms can be enlarged to increase food production. Efficient farming supports a larger colony and reduces dependency on Earth. Water extraction and recycling systems need to grow with the colony. Advanced technologies ensure sufficient water supply. Scalable systems support the colony's expanding needs. Transportation infrastructure must accommodate increased activity. Additional rovers, drones, and transport vehicles are necessary. Expanding transport networks facilitates mobility and logistics. Communication networks require scalability to handle more data. Satellite constellations and ground stations can be expanded. Reliable communication supports the colony's growth. Medical facilities must be equipped to serve a larger population. More clinics and hospitals can be built as the colony grows. Comprehensive healthcare is crucial for well-being. Educational facilities need to expand to accommodate more residents. Schools, universities, and research centers support learning. Education is vital for personal and community development. Recreational areas and social spaces should grow with the colony. Parks, theaters, and sports facilities enhance quality of life. Expanding these areas fosters a vibrant community. Waste management systems must scale up to handle more waste. Advanced recycling and composting systems ensure sustainability. Effective waste management supports a clean environment. Housing infrastructure must be adaptable for population growth. New living units and expanded housing complexes are necessary. Providing comfortable homes is essential for colonist satisfaction. Industrial facilities must increase production capabilities. Factories and manufacturing plants support construction and maintenance. Expanding industry ensures resource availability. Governance structures need to evolve with the colony. Administrative offices and meeting spaces support effective management. Scalable governance ensures smooth operations. Research and development facilities should grow to foster innovation. Expanding labs and tech centers drive technological progress. Continuous innovation supports the colony's advancement. International collaboration enhances scalability efforts. Partnering with other countries and organizations accelerates growth. Global cooperation is key to successful expansion. Solar power potential on Mars is significant due to the planet's proximity to the Sun. Solar panels can harness this energy to power habitats and equipment. Ensuring efficient energy capture is crucial for sustainability. Mars receives about half the solar energy that Earth does. Advanced solar panel technology can maximize energy absorption. High-efficiency panels are essential for meeting energy needs. Dust accumulation on solar panels is a challenge. Regular cleaning systems and dust-resistant coatings are necessary. These measures ensure continuous power generation. Energy storage is vital for consistent power supply. Batteries and other storage solutions can store excess energy. Stored energy can be used during dust storms and nighttime. Flexible solar panels can be deployed quickly. These panels are lightweight and adaptable to various surfaces. Flexibility supports rapid infrastructure development. Solar farms can provide large-scale energy solutions. These farms consist of numerous interconnected panels. Scaling up solar farms supports colony expansion. Solar-powered vehicles reduce reliance on other energy sources. Rovers and drones equipped with solar panels have extended operational ranges. This independence enhances mobility and exploration. Innovative designs like solar concentrators increase efficiency. These devices focus sunlight onto smaller, high-efficiency cells. Concentrated solar power boosts energy output. Solar panels can be integrated into habitat structures. Rooftop and wall-mounted panels maximize space usage. Integrated designs enhance overall energy efficiency. Tracking systems can optimize solar panel orientation. Automated systems adjust panels to follow the sun's path. Optimal alignment increases energy capture throughout the day. Combining solar power with other energy sources provides reliability. Hybrid systems ensure continuous power even during low sunlight. Diversified energy strategies enhance resilience. Research into new solar technologies continues to advance. Innovations in materials and designs improve performance. Continuous development supports the evolving energy needs of the colony. Solar power supports sustainable living on Mars. It reduces the need for imported fuels and resources. Harnessing solar energy is key to self-sufficiency. Collaborative efforts accelerate solar technology development. Sharing research and resources enhances efficiency. International cooperation drives innovation in solar power solutions. Expanding solar infrastructure supports long-term colonization. As the colony grows, scalable solar solutions ensure adequate power. Investing in solar technology is crucial for Mars's future. Nuclear energy options are essential for reliable power on Mars. Unlike solar power, nuclear energy provides a constant supply. This consistency is crucial during dust storms and long Martian nights. Small modular reactors, SMRs, are a promising solution. They are compact, efficient, and can be transported to Mars. SMRs offer scalable power options for growing colonies. Nuclear reactors can operate independently of sunlight. This independence ensures continuous energy production. Reliable power supports life support systems and other critical operations. Advanced reactors use fuel efficiently and produce less waste. Innovations in reactor design enhance safety and performance. Efficient fuel use extends the operational life of reactors. Heat generated by nuclear reactors can be used for multiple purposes. It can provide warmth in habitats and support industrial processes. Utilizing waste heat improves overall energy efficiency. Reactor designs for Mars prioritize safety. Built-in safeguards and passive cooling systems reduce risk. Ensuring reactor safety is paramount for crew protection. Nuclear energy can power high-demand systems like water extraction and production facilities. Reliable energy supports essential infrastructure. This stability is key to long-term sustainability. Developing nuclear propulsion systems enhances space travel. Nuclear-powered rockets can reduce travel time between Earth and Mars. Faster travel supports more frequent missions and cargo transport. International cooperation can accelerate nuclear energy development. Sharing expertise and resources improves reactor designs. Collaborative efforts enhance the viability of nuclear power on Mars. Radioisotope thermoelectric generators, RTGs, provide another nuclear option. RTGs use the heat from radioactive decay to generate electricity. They are reliable and have been used in space missions for decades. RTGs are ideal for powering remote scientific instruments and rovers. Their long lifespan supports extended missions. RTGs ensure that critical research continues without interruption. Nuclear energy supports the production of synthetic fuels. Reactors can power chemical processes to create fuel from local resources. This capability reduces dependency on Earth for fuel supplies. Implementing nuclear energy requires robust regulatory frameworks. Safety protocols and international standards ensure responsible use. Establishing these frameworks is critical for mission approval. Public perception of nuclear energy must be managed carefully. Clear communication about safety measures and benefits is essential. Building trust supports the acceptance of nuclear technology. Investing in nuclear energy options is crucial for Mars colonization. Reliable and continuous power enables sustainable living. Nuclear energy is a cornerstone of long-term human presence on Mars. Alternative energy sources are vital for diversifying Mars's power supply. Wind energy is one potential option. Though Mars has a thin atmosphere, high wind speeds can still generate power. Wind turbines must be specially designed for Martian conditions. Lightweight and efficient turbines can harness this energy. Implementing wind power adds to the colony's energy mix. Geothermal energy offers another alternative. Heat from beneath Mars' surface can be tapped for power. Geothermal plants provide a consistent and reliable energy source. Exploring volcanic areas can reveal geothermal hotspots. These sites can be prime locations for energy extraction. Utilizing geothermal heat supports a stable energy supply. Hydrogen fuel cells offer a portable and efficient energy solution. These cells convert hydrogen and oxygen into electricity and water. Fuel cells are ideal for mobile units and backup power. Producing hydrogen on Mars involves water electrolysis. Solar or nuclear power can drive this process. Hydrogen production supports both energy and fuel needs. Thermal energy storage can capture excess heat. This heat can be used during colder periods or at night. Efficient storage systems ensure continuous energy availability. Compressed air energy storage is another innovative approach. Excess energy compresses air, which is later released to generate power. This method provides a flexible energy storage option. Bioenergy from Martian-grown biomass can support small-scale power needs. Algae and other fast-growing plants can be converted into biofuel. Bioenergy integrates with sustainable agricultural practices. Organic waste can also be processed into biogas. Anaerobic digestion produces methane for energy use. This process supports waste management and energy production. Integrating multiple energy sources enhances resilience. A hybrid energy system can adapt to varying conditions. This flexibility ensures a stable and reliable power supply. Research into new materials can improve energy technologies. Advanced materials enhance the efficiency and durability of energy systems. Continuous innovation drives progress in alternative energy. Collaborating with Earth-based researchers accelerates development. Sharing knowledge and breakthroughs improves technology adoption. International partnerships support Mars energy infrastructure. Testing alternative energy systems on Earth ensures readiness. Simulations and prototypes refine designs for Martian deployment. Rigorous testing guarantees reliable performance. Investing in alternative energy sources diversifies Mars's power supply. A varied energy mix ensures sustainability and resilience. Exploring all options is key to a successful Mars colony. Energy storage solutions are crucial for maintaining a stable power supply on Mars. Efficient storage systems ensure that energy is available when needed. This reliability supports all aspects of colony life. Batteries are a primary method of energy storage. Lithium-ion batteries are popular due to their high energy density. They are capable of storing significant amounts of power in a compact form. Flow batteries offer an alternative with scalability advantages. These batteries use liquid electrolytes stored in external tanks. Flow batteries can be easily expanded to store more energy. Thermal energy storage captures excess heat for later use. Molten salts or other materials can retain heat efficiently. This stored thermal energy can be converted back to electricity when needed. Compressed air energy storage utilizes surplus power to compress air. The compressed air is stored in large underground chambers. When energy demand is high, the air is released to drive turbines. Flywheels provide a mechanical energy storage option. They store energy by spinning at high speeds. When power is needed, the kinetic energy is converted back to electricity. Hydrogen storage involves producing hydrogen through electrolysis. The hydrogen can be stored in tanks and used in fuel cells. This method supports both energy storage and fuel needs. Supercapacitors offer rapid charging and discharging capabilities. They store energy electrostatically, which allows for quick release. Supercapacitors complement other storage methods by handling short bursts of demand. Pumped hydro storage, though challenging on Mars, remains a viable concept. Water is pumped to a higher elevation using excess energy. It is then released to generate power through turbines. Solid-state batteries are emerging as a promising technology. They offer higher energy densities and improved safety over traditional batteries. Solid-state technology could revolutionize energy storage. Energy storage solutions must be integrated into the colony's power grid. This integration ensures a seamless transition between energy production and consumption. Efficient management systems are essential for optimal performance. Research into new materials and technologies continues to advance storage capabilities. Innovations can lead to more efficient and longer-lasting storage solutions. Continuous improvement is key to supporting the colony's growth. Collaborative efforts enhance the development of energy storage systems. Sharing research and resources accelerates technological advancements. International partnerships drive progress and implementation. Testing storage solutions on Earth simulates Martian conditions. These tests help refine designs and ensure reliability. Validating systems on Earth guarantees their effectiveness on Mars. Investing in diverse energy storage solutions ensures a resilient power supply. A robust storage infrastructure supports all aspects of colony life. Reliable energy storage is fundamental to sustainable living on Mars. Efficiency and conservation are essential for sustainable living on Mars. Optimizing resource use ensures the colony's longevity and success. Every system must be designed with these principles in mind. Energy-efficient appliances and systems reduce overall power consumption. Advanced insulation and lighting technologies minimize waste. These innovations contribute to a more sustainable habitat. Water conservation techniques are crucial in the dry Martian environment. Low-flow fixtures and efficient recycling systems help preserve water. Maximizing water use efficiency supports long-term survival. Agricultural practices must focus on conserving resources. Precision farming techniques use sensors to monitor and optimize water and nutrient use. Efficient agriculture ensures a steady food supply with minimal waste. Recycling and reusing materials reduce the need for new resources. Advanced recycling technologies can process a wide range of materials. This approach minimizes waste and supports a circular economy. Energy-efficient transportation reduces the colony's carbon footprint. Electric vehicles and optimized transport routes conserve energy. Efficient logistics are essential for daily operations. Smart grid technology enhances energy distribution and conservation. Automated systems manage energy flow and reduce losses. A smart grid supports a reliable and efficient power supply. Habitat design incorporates passive solar heating and cooling. These techniques use the sun's energy to regulate temperatures naturally. Passive design reduces the need for additional heating and cooling. Thermal insulation is critical for maintaining stable temperatures. High-performance materials keep habitats warm in the cold Martian climate. Effective insulation reduces energy consumption. Renewable energy sources like solar and wind power are central to sustainability. Using these resources efficiently reduces dependence on imported fuels. Renewable energy supports a self-sufficient colony. Data-driven decision-making improves resource management. Sensors and analytics provide real-time insights into resource use. Informed decisions enhance efficiency and conservation efforts. Community involvement is vital for promoting efficiency and conservation. Education and awareness programs encourage sustainable practices. Collective effort ensures the success of conservation initiatives. Technological innovation drives continuous improvement in efficiency. Research and development lead to new solutions for conserving resources. Ongoing innovation is key to long-term sustainability. Collaborative efforts with Earth-based researchers enhance efficiency strategies. Sharing knowledge and best practices accelerates progress. Global cooperation supports Mars' sustainability goals. Regular maintenance and upgrades keep systems running efficiently. Preventative maintenance reduces the risk of breakdowns and energy loss. Ensuring optimal performance is essential for all systems. Rovers and surface vehicles are essential for exploration and logistics on Mars. These vehicles are designed to navigate the planet's rugged terrain. They play a crucial role in transporting equipment and conducting scientific research. Autonomous rovers are equipped with advanced navigation systems. These systems allow them to operate independently. Autonomous capabilities increase efficiency and reduce the need for constant human oversight. Solar-powered rovers utilize the abundant sunlight on Mars. Solar panels provide a sustainable energy source. This design supports long-duration missions without frequent recharging. Nuclear-powered rovers offer another reliable energy option. They can operate for extended periods in low-light conditions. This energy source is ideal for missions exploring shaded areas or during dust storms. Rovers are equipped with scientific instruments for data collection. These instruments analyze soil, rocks, and atmospheric conditions. Gathering this data is essential for understanding Mars' environment. Surface vehicles support construction and maintenance tasks. They transport materials, tools, and personnel across the colony. Efficient transport systems are critical for daily operations. Heavy-duty rovers are designed for transporting large payloads. They move building materials and heavy equipment needed for habitat construction. These vehicles are integral to infrastructure development. Robust suspension systems enable rovers to traverse rough terrain. Advanced wheel designs and suspension improve stability. This capability allows rovers to access challenging areas for exploration. Modular design allows for versatile use of rovers. Interchangeable parts and tools can be adapted for different tasks. This flexibility enhances their functionality and utility. Remote-controlled rovers enable precise operations. Human operators can control these vehicles from a safe distance. This control is crucial for delicate or hazardous tasks. Communication systems ensure constant contact between rovers and the base. Reliable links are essential for coordinating missions and data transfer. Strong communication networks support effective operations. Maintenance and repair facilities keep rovers operational. Regular checkups and servicing prevent breakdowns. Ensuring rover reliability is vital for ongoing exploration. Rovers contribute to life support by transporting water and supplies. They deliver essential resources to different parts of the colony. Efficient logistics support the colony's sustainability. Innovative designs continue to improve rover capabilities. Research and development focus on enhancing durability and efficiency. Continuous innovation drives the advancement of surface vehicles. International collaboration enhances rover technology development. Sharing expertise and resources accelerates progress. Global partnerships are key to achieving success in Mars exploration. Aerial drones and aircraft are vital for Mars exploration and logistics. They provide a unique vantage point for mapping and surveying the terrain. These aerial vehicles extend the reach of ground-based rovers. Drones are equipped with high-resolution cameras and sensors. These tools capture detailed images and data from above. This aerial perspective enhances scientific research and planning. Solar-powered drones utilize the Martian sunlight for extended flights. Solar panels recharge their batteries, allowing for long-duration missions. This renewable energy source supports continuous operations. Autonomous navigation systems enable drones to operate independently. They can follow pre-programmed routes and avoid obstacles. Autonomous drones reduce the need for constant human control. Drones can quickly cover large areas, making them ideal for scouting missions. They identify interesting sites for further exploration by rovers. Speed and agility are key advantages of aerial drones. Communication relays are another important function of drones. They act as mobile signal boosters, extending communication networks. Reliable communication is essential for coordinating missions. Lightweight aircraft provide another layer of exploration capability. These aircraft can carry larger payloads than drones. They support various missions, including cargo transport and scientific research. Vertical takeoff and landing, VTOL technology, allows aircraft to operate in diverse environments. VTOL aircraft can land on uneven terrain, making them versatile tools. This capability enhances their deployment options. Fixed-wing aircraft offer efficient long-distance travel. They can cover vast areas quickly, ideal for extensive surveys. Fixed-wing designs complement the capabilities of drones and VTOL aircraft. Aerial vehicles support emergency response and rescue operations. They can quickly reach and assess remote or hazardous areas. Fast response times are crucial for colony safety. Drones equipped with LiDAR provide detailed topographical maps. LiDAR technology offers precise measurements of the Martian surface. These maps are essential for planning construction and navigation. Multi-mission drones can carry interchangeable payloads. These payloads include cameras, sensors, and communication equipment. Versatile designs maximize the utility of each drone. Aerial refueling systems extend the operational range of drones and aircraft. This capability allows for longer missions without returning to base. Extended range supports comprehensive exploration. Maintenance and repair facilities ensure aerial vehicles remain operational. Regular servicing prevents malfunctions and extends lifespan. Reliable maintenance is critical for mission success. Continued innovation enhances the performance of drones and aircraft. Research focuses on improving flight efficiency and payload capacity. Ongoing development drives the evolution of aerial exploration tools. Transport for cargo and supplies is crucial for the functioning of a Mars colony. Efficient logistics systems ensure that all necessary materials are available. This includes food, water, construction materials, and scientific equipment. Cargo rovers are designed to handle heavy loads. These robust vehicles can transport large quantities of supplies across the Martian terrain. Their durability and capacity make them essential for building and maintaining the colony. Automated cargo systems enhance efficiency and reduce the need for human labor. Autonomous vehicles can deliver supplies to remote locations. Automation streamlines logistics and frees up personnel for other tasks. Modular cargo containers allow for versatile transport options. These containers can be easily transferred between different vehicles. Standardized containers simplify loading and unloading processes. Aerial drones also play a role in cargo transport. They can quickly deliver small, urgent supplies to distant locations. This rapid delivery system supports time-sensitive missions and emergencies. Larger aircraft can transport bulk supplies over long distances. They provide a crucial link between different parts of the colony. Aerial transport reduces the time and effort needed for ground travel. Efficient storage solutions are vital for managing supplies. Warehouses and storage units are strategically placed throughout the colony. Proper storage ensures that supplies are organized and accessible. Energy-efficient vehicles are essential for sustainable logistics. Solar-powered and electric transport reduce reliance on imported fuels. This sustainability is key to the colony's long-term viability. Transport infrastructure includes well-maintained roads and pathways. Clear routes facilitate smooth movement of cargo and personnel. Infrastructure planning supports efficient transport operations. Real-time tracking systems monitor the movement of supplies. These systems ensure that all cargo is accounted for and reaches its destination. Tracking technology enhances security and efficiency. Scheduled maintenance keeps transport vehicles in optimal condition. Regular servicing prevents breakdowns and prolongs the lifespan of vehicles. Maintenance is critical for reliable transport operations. Collaborative logistics planning involves all parts of the colony. Coordinated efforts ensure that supplies are distributed where they are needed most. Effective communication is essential for successful logistics. Emergency transport capabilities are crucial for dealing with crises. Dedicated vehicles and protocols ensure rapid response to emergencies. Preparedness supports the colony's resilience and safety. Innovative transport technologies continue to evolve. Research into new materials and designs improves efficiency and capacity. Continuous improvement drives the advancement of logistics systems. International cooperation enhances transport logistics. Sharing knowledge and resources with global partners accelerates development. Collaborative efforts support the overall success of Mars colonization. Human mobility and exploration are key to unlocking Mars's potential. Advanced mobility systems allow astronauts to explore the Martian surface. These systems are essential for scientific research and habitat expansion. Personal mobility units enhance individual movement across rough terrain. These units are lightweight and powered by renewable energy. They provide flexibility and freedom for daily activities. Rover missions enable extensive exploration beyond the immediate habitat. Crewed rovers offer safety and support for long-distance travel. These vehicles are equipped with life support systems for extended missions. Exoskeletons can assist astronauts in performing physically demanding tasks. These wearable devices enhance strength and reduce fatigue. Exoskeletons are particularly useful for construction and repair work. Mapping and navigation tools are crucial for safe exploration. GPS-like systems and detailed maps guide astronauts through unfamiliar areas. Accurate navigation ensures efficient and safe travel. Portable habitats support longer exploration missions. These temporary shelters provide protection and life support. Portable habitats extend the range and duration of field missions. All-terrain vehicles are designed for Mars' diverse landscape. These versatile vehicles handle rocks, dust, and slopes with ease. All-terrain capability is vital for thorough exploration. Scientific instruments are carried on exploration missions to gather data. Portable labs and sensors enable on-site analysis. This immediate data collection enhances research efficiency. Safety protocols are essential for exploration missions. Emergency supplies and communication links are always maintained. Preparedness for unforeseen events ensures mission success. Team coordination is crucial for effective exploration. Crew members work together to cover more ground and share tasks. Strong teamwork enhances productivity and safety. Training programs prepare astronauts for the challenges of Mars mobility. Simulations and practice missions build skills and confidence. Comprehensive training is essential for mission readiness. Innovative mobility solutions are constantly being developed. Research into new technologies and materials drives progress. Continuous improvement expands the possibilities for exploration. Collaboration with international partners enriches exploration efforts. Sharing knowledge and resources enhances mission planning. Global cooperation supports a unified approach to Mars exploration. Human mobility is integral to the success of Mars colonization. Advanced systems and technologies ensure that astronauts can explore and thrive. Mobility and exploration drive discovery and development on Mars. Future missions will continue to expand human presence on Mars. Each step forward brings new insights and opportunities. Human mobility and exploration are the cornerstones of a sustainable Martian future. Developing a transport network on Mars is essential for efficient logistics. A well-planned network supports the movement of people and goods. It ensures that resources are distributed where they are needed most. Transport hubs serve as central points for distribution. These hubs connect various parts of the colony, facilitating easy transfer of cargo. Strategically placed hubs enhance the network's efficiency. Roads and pathways must be constructed to connect key locations. Durable materials and regular maintenance ensure these routes remain accessible. Well-maintained roads support continuous transport operations. Automated systems streamline the transport network. Autonomous vehicles and drones handle routine deliveries. Automation reduces the need for human intervention and increases efficiency. Intermodal transport integrates different modes of transportation. Combining rovers, drones, and aircraft maximizes flexibility. Intermodal systems optimize the use of available resources. Energy infrastructure supports the transport network. Charging stations for electric vehicles are essential. Renewable energy sources like solar and wind power these stations. Safety protocols are critical for a reliable transport network. Emergency response plans and safety measures protect both people and cargo. Ensuring safety is a top priority. Data management systems monitor transport activities. Real-time tracking and analytics optimize logistics. These systems provide valuable insights for improving efficiency. Scalability is important for future growth. The transport network must be able to expand as the colony grows. Scalable systems accommodate increased demand over time. Collaboration with international partners enhances network development. Sharing technology and expertise accelerates progress. Global cooperation is key to building a robust transport network. Sustainable practices ensure the network's longevity. Efficient use of resources and minimizing environmental impact are essential. Sustainable transport supports the colony's long-term goals. Public involvement in planning can improve the network. Feedback from colonists helps identify needs and challenges. Community input ensures the network meets everyone's needs. Technological innovation drives continuous improvement. Research into new materials and designs enhances transport systems. Innovation ensures the network remains cutting edge. Regular assessments and upgrades keep the network efficient. Periodic reviews identify areas for improvement. Upgrading infrastructure maintains high performance. A well-developed transport network is crucial for Mars colonization. It supports all aspects of daily life and mission success. Investing in transport infrastructure paves the way for a thriving colony. Governance and laws are fundamental to maintaining order on Mars. Establishing a legal framework ensures fair and effective management. Clear laws and regulations guide the colony's growth and development. A central governing body is necessary for decision-making. This body oversees the colony's administration and implements policies. Effective governance supports a stable and organized society. Legal systems must address property rights and resource management. Defining ownership and usage rights prevents conflicts. Fair distribution of resources ensures equitable access for all. Dispute resolution mechanisms are essential for maintaining harmony. Mediation and arbitration processes help resolve conflicts. These mechanisms ensure justice and fairness within the colony. Safety and security regulations protect inhabitants and property. Laws regarding emergency procedures and safety standards are crucial. Ensuring compliance with these regulations enhances overall safety. Environmental laws preserve Mars' unique ecosystem. Regulations on waste disposal and resource usage minimize environmental impact. Sustainable practices are essential for long-term habitation. Workplace laws ensure fair labor practices. Regulations on working conditions, hours, and wages protect workers' rights. A fair labor system supports the well-being of the colony's workforce. Immigration laws manage the influx of new settlers. Clear criteria and processes for residency ensure orderly population growth. These laws help integrate newcomers smoothly into the colony. Public health laws are vital for community well-being. Regulations on sanitation, healthcare, and disease prevention protect public health. Comprehensive health policies ensure a healthy population. Education laws promote knowledge and skill development. Regulations on compulsory education and curriculum standards support learning. Education is key to the colony's advancement and innovation. Laws on innovation and intellectual property encourage creativity. Protecting intellectual property rights fosters research and development. Innovation drives progress and technological advancement. Communication laws regulate information exchange and privacy. Ensuring secure and reliable communication networks is crucial. Privacy laws protect personal data and information. Economic regulations guide the colony's financial system. Laws on trade, taxation, and commerce support economic stability. A robust economic framework is essential for growth and prosperity. Collaboration with Earth-based legal systems harmonizes regulations. Aligning laws with international standards facilitates cooperation. Global legal alignment supports seamless interaction with Earth. Continuous review and adaptation of laws ensure they remain relevant. Regular updates address new challenges and opportunities. Dynamic governance and legal systems support a thriving Mars colony. Social structure and community building are essential for a cohesive Mars colony. Establishing a sense of community fosters collaboration and mutual support. Strong social bonds enhance the overall well-being of colonists. Diverse social groups contribute to a rich community life. Encouraging cultural exchange and inclusion strengthens social ties. Celebrating diversity promotes understanding and harmony. Community centers serve as hubs for social interaction. These spaces host events, meetings, and recreational activities. Accessible community centers support a vibrant social life. Educational programs are crucial for knowledge sharing and development. Schools, workshops, and training sessions build skills and foster growth. Lifelong learning opportunities enhance individual and community potential. Healthcare services support physical and mental well-being. Clinics and counseling centers provide essential medical and psychological care. Access to healthcare ensures a healthy and resilient population. Recreational activities offer relaxation and enjoyment. Sports, arts, and hobbies provide outlets for creativity and stress relief. Recreational programs contribute to a balanced and fulfilling life. Volunteer organizations enable community involvement. Residents can contribute to various initiatives and support each other. Volunteering fosters a sense of purpose and belonging. Effective communication channels keep the community informed. Newsletters, forums, and meetings ensure transparency and engagement. Open communication builds trust and unity. Leadership opportunities empower residents to take active roles. Encouraging participation in governance and community projects promotes leadership development. Shared leadership responsibilities enhance collective decision-making. Social events and festivals celebrate milestones and traditions. These gatherings strengthen community bonds and cultural heritage. Regular events keep the social fabric strong. Support networks provide assistance in times of need. Peer groups and community support services offer help and encouragement. Strong support systems ensure no one feels isolated or neglected. Public spaces enhance social interaction and community life. Parks, plazas, and common areas are designed for gatherings and leisure. Well-designed public spaces facilitate spontaneous and planned social activities. Conflict resolution mechanisms maintain harmony within the community. Mediation and dialogue encourage peaceful solutions to disagreements. Effective conflict resolution fosters a cooperative and respectful environment. Youth programs engage the younger generation in community life. Educational and recreational activities for children and teens support their development. Involving youth ensures the future vitality of the colony. Community building initiatives are ongoing and evolving. Regular assessments and feedback help improve social programs. Continuous efforts ensure the Mars colony remains a dynamic and supportive community. Cultural and recreational activities are vital for a thriving Mars colony. These activities provide relaxation, creativity, and social interaction. A well-rounded cultural life enhances the overall quality of life. Artistic expression is encouraged through various mediums: painting, sculpture, and digital art allow colonists to share their creativity. Art classes and galleries showcase local talent. Music plays a significant role in cultural activities. Community concerts, music lessons, and jam sessions bring people together. Music fosters a sense of unity and joy. Theatre and performance arts offer entertainment and creative outlets. Plays, improvisation, and dance performances engage the community. These activities provide both participants and audiences with enjoyment. Literary pursuits are supported through book clubs and writing workshops. Reading and storytelling sessions encourage intellectual growth. A community library provides resources and a quiet space for study. Sports and physical activities promote health and camaraderie. Soccer, basketball, and other team sports are organized regularly. Fitness classes and outdoor adventures keep the community active. Cultural festivals celebrate diverse traditions and heritage. Festivals include food, music, dance, and crafts from different cultures. These events promote understanding and appreciation of diversity. Recreational facilities offer spaces for various hobbies. Maker spaces, craft rooms, and gaming areas cater to diverse interests. These facilities provide tools and resources for creative projects. Outdoor activities make use of the unique Martian environment. Hiking, rock climbing, and exploration outings connect colonists with their surroundings. Outdoor recreation supports physical and mental well-being. Gardening and green spaces bring nature into daily life. Community gardens and greenhouses offer relaxation and fresh produce. Working with plants provides therapeutic benefits and sustains local food production. Virtual reality experiences offer immersive recreation. VR technology enables exploration of Earth and imaginative worlds. These experiences provide escape and entertainment in a confined environment. Cooking and culinary arts bring joy and cultural exchange. Cooking classes and communal meals highlight diverse cuisines. Sharing food fosters connections and celebrates cultural heritage. Educational workshops and lectures enhance knowledge and skills. Topics range from science and technology to arts and humanities. Lifelong learning opportunities keep the community engaged and informed. Community-driven projects encourage collaboration and innovation. Building projects, scientific research, and artistic collaborations unite colonists. These initiatives strengthen community bonds and drive progress. Family-friendly activities ensure all age groups are engaged. Playgroups, family outings, and intergenerational events build a cohesive community. Inclusive activities support family connections and community spirit. Celebrating milestones and achievements strengthens morale. Award ceremonies, anniversaries, and personal milestones are recognized. Acknowledging successes fosters pride and motivation within the colony. Education and knowledge sharing are pillars of a successful Mars colony. Continuous learning supports personal growth and community development. Diverse educational programs cater to all age groups. Schools provide structured learning for children. Curricula include science, mathematics, arts, and humanities. Education ensures the next generation is well prepared. Adult education programs offer skill development and career advancement. Workshops and courses cover technical skills, leadership, and personal development. Lifelong learning opportunities enrich the community. Libraries serve as knowledge hubs. They provide access to books, digital resources, and research materials. Libraries support both formal education and self-directed learning. Online courses and virtual classrooms expand educational reach. These platforms connect colonists with global experts and institutions. Online learning fosters global knowledge exchange. Research facilities encourage scientific exploration. Laboratories and research centers support innovative projects. Collaboration in research drives technological and scientific progress. Knowledge-sharing events promote community learning. Lectures, seminars, and discussion groups facilitate intellectual exchange. These events engage residents and spark new ideas. Mentorship programs pair experienced individuals with learners. Mentors provide guidance, support, and expertise. Mentorship strengthens skills and builds confidence. Cultural education preserves and celebrates diverse heritages. Programs explore history, traditions, and languages. Cultural knowledge enriches the community's identity. Technical training equips colonists with essential skills. Hands-on workshops teach engineering, programming, and maintenance. Practical skills are vital for daily operations and problem-solving. art and creativity are integrated into education. Art classes, music lessons, and creative writing foster expression. Creative education nurtures well-rounded individuals. Community projects provide real-world learning experiences. Collaborative initiatives in construction, agriculture, and technology apply classroom knowledge. Project-based learning enhances practical understanding. Environmental education emphasizes sustainability. Programs teach resource management, recycling, and ecological stewardship. Knowledge of environmental practices supports a sustainable colony. Knowledge-sharing platforms connect residents. Online forums, intranet systems, and social networks facilitate information exchange. Effective communication networks keep everyone informed. Education partnerships with Earth institutions enhance learning. Collaborations with universities and research organizations provide resources and expertise. These partnerships expand educational opportunities and drive innovation. Recognition of educational achievements motivates learners. Awards, certificates, and public acknowledgement celebrate progress. Recognition fosters a culture of learning and achievement. Integration with Earth societies is crucial for the success of a Mars colony. Strong connections foster collaboration and mutual support. This integration ensures that Mars benefits from Earth's advancements and resources. Regular communication with Earth keeps both worlds informed. News updates, scientific discoveries, and cultural exchanges maintain a close relationship. Effective communication strengthens bonds between the two planets. Trade agreements facilitate the exchange of goods and services. Mars can export unique resources and import essential supplies. Trade supports economic stability and growth for the colony. Joint scientific missions enhance research opportunities. Collaborative projects leverage expertise from both Earth and Mars. These missions drive innovation and expand knowledge. Cultural exchanges enrich both societies. Festivals, art exhibitions, and virtual tours share traditions and creativity. Cultural integration fosters understanding and appreciation. Educational partnerships connect students and educators. Exchange programs and joint courses provide diverse learning experiences. These partnerships enhance education on both planets. Shared governance models incorporate best practices from Earth. Legal frameworks and administrative structures benefit from global expertise. Governance integration ensures effective and fair management. Health and medical collaboration improves care standards. Sharing medical research, treatments, and technologies benefits public health. Integrated health systems provide better care for all. Environmental cooperation addresses global challenges. Joint efforts in sustainability and conservation protect both planets. Collaborative environmental strategies promote a healthy ecosystem. Economic integration creates opportunities for businesses. Companies can operate on both Earth and Mars, driving innovation and growth. Economic ties strengthen the overall prosperity of the colony. Social media platforms connect individuals across planets. Residents share experiences, ideas, and stories in real time. Social media fosters a sense of community and belonging. Crisis response and disaster management benefit from shared resources. Joint emergency plans and support systems enhance resilience. Cooperation ensures preparedness for any unforeseen events. Political alliances support stability and security. Diplomatic relations and treaties build trust and cooperation. Political integration promotes peace and mutual respect. Technological advancements are accelerated through collaboration. Sharing research and development efforts leads to breakthroughs. Technological integration drives progress and innovation. Cultural preservation efforts protect heritage and identity. Joint initiatives safeguard historical and cultural artifacts. Preserving culture ensures that traditions and history are honored. Continuous dialogue and collaboration build a strong, integrated relationship. This partnership supports the growth and development of both Earth and Mars. Together, we create a thriving interplanetary community. Funding and investment are critical for establishing and maintaining a Mars colony. Securing financial resources ensures the development of necessary infrastructure. Diverse funding sources provide stability and growth potential. Government funding plays a significant role in initial investments. Space agencies allocate budgets for research, development, and exploration. Public funding supports large-scale projects and international collaborations. Private investment drives innovation and commercial opportunities. Companies see potential in space tourism, mining, and research. Private funds accelerate technological advancements and entrepreneurial ventures. Public-private partnerships combine resources and expertise. These collaborations leverage the strengths of both sectors. Joint ventures enhance efficiency and reduce financial risks. Crowdfunding campaigns engage the public in space exploration. Enthusiasts and supporters contribute small amounts collectively. Crowdfunding fosters community involvement and broadens financial support. International funding pools resources from multiple countries. Cooperative efforts distribute costs and share benefits. Global investment strengthens the overall mission and fosters unity. Space-related bonds and securities attract institutional investors. Financial instruments provide long-term funding for space projects. These investments support sustainable growth and development. Venture capital firms seek high returns from space startups. They fund innovative companies with groundbreaking technologies. Venture capital drives the growth of the space industry. Tax incentives encourage investment in space activities. Governments offer benefits to companies investing in space exploration. These incentives stimulate economic growth and technological progress. Grants and scholarships support research and education. Funding for academic institutions advances scientific knowledge. Educational investments ensure a skilled workforce for the future. Revenue from space tourism provides a steady income stream. Tours to Mars attract wealthy individuals and adventure seekers. Tourism revenue funds further exploration and infrastructure. Licensing and intellectual property rights generate income. Patents and technologies developed for Mars have Earth applications. Licensing agreements provide ongoing revenue. Corporate sponsorships offer branding opportunities in space. Companies invest in exchange for marketing and promotional benefits. Sponsorships increase visibility and support financial needs. Long-term financial planning ensures sustainable development. Diversified investments and strategic budgeting promote stability. Careful planning prepares the colony for future challenges. Continuous investment fosters a thriving and self-sustaining Mars colony. Securing diverse funding sources ensures ongoing growth and prosperity. Together, we build a stable and prosperous interplanetary future. Economic models and sustainability are key to a thriving Mars colony. Developing a robust economy ensures long-term viability. Sustainable practices support environmental and resource management. A mixed economy combines public and private sector roles. Government initiatives provide stability, while private enterprises drive innovation. This balance fosters a resilient and dynamic economic environment. Resource-based economies utilize Mars' natural assets. Mining and resource extraction offer valuable materials for trade. Efficient resource management ensures economic growth and sustainability. Circular economies focus on recycling and reusing materials. Minimizing waste and maximizing resource efficiency are central goals. Circular practices support environmental health and reduce dependency on imports. Agroeconomies emphasize local food production. Advanced agricultural techniques ensure a steady food supply. Sustainable farming practices contribute to food security and economic stability. Service-based economies offer diverse opportunities. Education, healthcare, and technology services create jobs and support quality of life. A strong service sector enriches the community and drives growth. Innovation hubs stimulate economic development. Research and development centers attract talent and investment. Innovation fuels progress and keeps the economy competitive. Trade networks connect Mars with Earth and other space outposts. Importing essential goods and exporting unique resources balance trade. Strong trade relations enhance economic resilience. Financial institutions provide essential services. Banks, investment firms, and insurance companies support economic activities. Robust financial systems ensure stability and growth. Sustainable tourism generates revenue and promotes awareness. Eco-friendly tourism practices protect the environment. Tourism income funds further exploration and infrastructure. Workforce development focuses on education and training. Skilled labor is crucial for economic progress and innovation. Continuous learning opportunities ensure a competent workforce. Entrepreneurial support fosters new business creation. Incentives and resources encourage startups and small businesses. Entrepreneurship drives economic diversity and innovation. Energy economies leverage renewable sources. Solar, wind, and nuclear energy provide reliable power. Sustainable energy practices ensure long-term economic health. Collaborative economic models integrate global efforts. Partnerships with Earth-based institutions and other colonies enhance growth. Collaboration spreads risks and shares rewards. Adaptive economic policies respond to changing conditions. Flexible regulations and proactive planning ensure economic resilience. Adaptability prepares the colony for future challenges and opportunities. Trade and commerce are vital for a self-sustaining Mars colony. Establishing robust trade networks ensures the flow of goods and services. Effective commerce supports economic growth and stability. Interplanetary trade connects Mars with Earth and other space settlements. Exporting Martian resources and importing essential supplies create a balanced trade ecosystem. These exchanges enhance economic resilience and growth. A diverse marketplace offers various goods and services. Local businesses provide everything from food to technology. A thriving marketplace supports the community's needs and drives innovation. Digital commerce platforms facilitate transactions. Online marketplaces and payment systems streamline buying and selling. These platforms connect buyers and sellers efficiently. Regulations ensure fair trade practices. Clear laws and standards protect consumers and businesses. Regulatory frameworks maintain market integrity and transparency. Supply chain management is crucial for efficient trade. Coordinating logistics and inventory ensures timely delivery of goods. Advanced supply chain systems optimize trade operations. Customs and tariffs manage the flow of goods between planets. These measures protect local industries and regulate imports. Effective customs policies balance trade and revenue. Financial services support trade and commerce activities. Banks, credit unions, and payment processors facilitate transactions. Strong financial systems underpin commercial stability. Investment opportunities attract capital to the colony. Encouraging investments in local businesses stimulates economic growth. Investment incentives promote business development and innovation. Collaborative trade agreements strengthen economic ties. Partnerships with Earth and other colonies expand market access. Collaborative agreements enhance trade efficiency and cooperation. Business incubators support new ventures. Providing resources and mentorship helps startups succeed. Incubators drive economic diversity and job creation. Marketing and advertising promote local businesses. Effective strategies increase visibility and attract customers. Marketing efforts boost sales and economic activity. Consumer protection laws safeguard residents. Ensuring product safety and fair pricing builds trust. Strong consumer protections enhance market confidence. E-commerce expands market reach. Online stores and delivery services cater to diverse consumer needs. E-commerce platforms support convenience and accessibility. Continuous market analysis informs economic strategies. Monitoring trends and consumer behavior guides decision-making. Data-driven insights optimize trade and commerce policies. Job creation and a robust labor market are essential for Mars colonization. A diverse range of employment opportunities supports economic stability. Developing a skilled workforce ensures the colony's growth and sustainability. Local industries drive job creation. Mining, agriculture, and manufacturing sectors provide numerous roles. These industries form the backbone of the colony's economy. Education and training programs prepare residents for the labor market. Vocational schools and apprenticeships develop necessary skills. Continuous learning opportunities enhance workforce capabilities. High-tech jobs emerge from innovation and research. Roles in engineering, software development, and scientific research attract talent. These jobs drive technological advancements and economic growth. Healthcare positions are crucial for community well-being. Doctors, nurses, and medical technicians ensure access to quality care. A strong healthcare sector supports a healthy population. Construction and infrastructure projects create employment. Building habitats, roads, and facilities requires skilled labor. These projects are vital for the colony's development. Service industries offer a wide range of job opportunities. Retail, hospitality, and entertainment sectors enhance quality of life. These industries provide everyday services and social engagement. Entrepreneurship fosters new business creation. Supporting startups with resources and mentorship encourages innovation. Small businesses diversify the economy and create jobs. Remote work opportunities connect Mars with global markets. Telecommuting roles in IT, design, and consulting leverage global expertise. Remote work expands job options and economic reach. Public sector jobs ensure effective governance. Roles in administration, law enforcement, and education support colony operations. A strong public sector underpins community stability. Environmental management creates specialized roles. Conservation, waste management, and sustainable practices require dedicated workers. These roles protect the Martian environment and resources. Agricultural jobs ensure food security. Farmers, horticulturists, and food scientists develop sustainable farming methods. A thriving agricultural sector supports local food production. Energy sector roles focus on renewable resources. Solar technicians, nuclear engineers, and energy analysts maintain power systems. Reliable energy supports all aspects of colony life. Collaboration with Earth creates additional job opportunities. Joint ventures and research projects require a skilled workforce. International cooperation expands the labor market. Future-oriented planning ensures ongoing job creation. Anticipating economic trends and technological advancements guides employment strategies. Proactive planning supports a dynamic and resilient labor market. Economic independence from Earth is a critical goal for a sustainable Mars colony. Developing local industries and resources reduces reliance on imports. Achieving self-sufficiency ensures long-term viability. Local resource extraction provides essential materials. Mining operations yield metals, minerals, and other valuable resources. Utilizing Martian resources supports construction and manufacturing. Advanced manufacturing capabilities enable local production. 3D printing and automated factories produce tools, parts, and goods. Local manufacturing reduces dependency on Earth-based supplies. Agricultural self-sufficiency ensures a stable food supply. Hydroponic systems, greenhouses, and vertical farming support local food production. Sustainable agriculture practices enhance food security. Renewable energy sources power the colony. Solar, wind, and nuclear energy systems provide reliable power. Energy independence supports all aspects of daily life and operations. Water recycling and extraction reduce the need for imported water. Advanced filtration and desalination technologies ensure a steady water supply. Efficient water management is crucial for independence. Healthcare infrastructure provides essential medical services. Local production of pharmaceuticals and medical supplies supports healthcare needs. A robust healthcare system ensures community well-being. Educational institutions develop a skilled workforce. Schools, universities, and training programs prepare residents for various roles. A well-educated population drives economic growth and innovation. Technological innovation fosters self-sufficiency. Research and development centers focus on solving local challenges. Continuous innovation supports independence and resilience. Strong governance ensures effective resource management. Local policies and regulations guide sustainable practices. Effective governance supports economic stability and growth. Financial systems facilitate local commerce. Banks, credit unions, and investment firms support economic activities. A robust financial sector underpins economic independence. Cultural industries contribute to local identity and economy. Arts, entertainment, and cultural events enrich community life. Cultural activities support social cohesion and economic diversity. Trade with other space settlements enhances economic stability. Exporting goods and services creates revenue streams. Interplanetary trade fosters economic resilience and growth. Local entrepreneurship drives innovation and job creation. Supporting startups and small businesses fosters economic diversity. Entrepreneurship contributes to a dynamic and resilient economy. Long-term planning and investment ensure sustainable development. Strategic initiatives focus on resource management and technological advancements. Proactive planning supports ongoing economic independence. Environmental preservation on Mars is essential for sustainable colonization. Protecting the Martian environment ensures the long-term health of the colony. Careful management of natural resources is critical. Preventing contamination of Martian soil and water is a priority. Strict protocols for waste disposal and habitat maintenance minimize environmental impact. Clean operations protect Mars' pristine landscape. Sustainable resource extraction methods reduce environmental damage. Responsible mining practices and efficient use of materials preserve natural habitats. Sustainable extraction supports long-term viability. Renewable energy sources help minimize environmental footprint. Solar, wind, and nuclear energy reduce reliance on fossil fuels. Clean energy solutions protect Mars' environment. Water conservation is vital for environmental sustainability. Recycling and efficient usage prevent depletion of local water sources. Conservation efforts ensure a steady water supply for all needs. Habitat design incorporates environmental considerations. Buildings are constructed with minimal impact on the surrounding landscape. Eco-friendly architecture supports environmental preservation. Agricultural practices focus on sustainability. Hydroponics and vertical farming use less land and water. Sustainable farming techniques protect the Martian ecosystem. Waste management systems prioritize recycling and reduction. Advanced technologies convert waste into useful resources. Effective waste management reduces environmental pollution. Research and monitoring track environmental health. Continuous data collection informs conservation efforts. Ongoing research helps adapt practices to protect Mars' environment. Education programs raise awareness about environmental preservation. Colonists learn about sustainable practices and their importance. Knowledgeable residents contribute to environmental efforts. Biodiversity conservation plans protect potential Martian life forms. Preserving native species, if any exist, is a key consideration. Biodiversity efforts ensure the integrity of Mars' ecosystem. Green spaces within habitats enhance environmental quality. Parks and gardens improve air quality and provide recreational areas. Green spaces support mental health and environmental benefits. Collaboration with Earth-based organizations enhances preservation efforts. Shared knowledge and resources improve conservation strategies. International cooperation supports global environmental goals. Innovative technologies drive environmental preservation. Research into new materials and methods reduces ecological impact. Technological advancements support sustainable colonization. Long-term planning ensures the continued protection of Mars. Strategic initiatives focus on balancing development and conservation. Proactive planning supports a healthy and sustainable environment for future generations. Ethical considerations of colonization are paramount for responsible expansion. Addressing these concerns ensures a fair and just approach to inhabiting Mars. Ethical frameworks guide decisions and actions. Respecting Martian environments is a key ethical concern. Preserving the planet's natural state prevents irreversible damage. Responsible exploration minimizes environmental impact. The potential discovery of Martian life forms raises significant ethical questions. Protecting any indigenous life is a moral obligation. Preventing contamination safeguards both Martian and Earth life. Ensuring equitable access to resources and opportunities is essential. Fair distribution of land, water, and materials supports justice. Equitable policies promote harmony within the colony. The rights and well-being of all colonists must be prioritized. Providing safe living conditions and fair labor practices is crucial. Protecting human rights fosters a healthy and just society. Informed consent is critical for participants in the colonization effort. Transparent communication about risks and benefits ensures autonomy. Ethical recruitment practices respect individual choices. Cultural preservation is important for maintaining identity. Encouraging diverse traditions and practices enriches the community. Cultural respect fosters inclusivity and mutual understanding. Long-term sustainability must be a core ethical principle. Practices that ensure the colony's viability benefit future generations. Ethical planning balances growth with resource conservation. Privacy rights need protection in a closely monitored environment. Secure data management and respectful surveillance practices are essential. Upholding privacy maintains trust and individual dignity. Collaborative decision-making promotes ethical governance. Involving colonists in policy formation ensures representation. Democratic processes support fairness and transparency. Addressing potential conflicts ethically is crucial. Mediation and peaceful resolution techniques prevent violence. Fair conflict resolution maintains social harmony. Global cooperation must be guided by ethical principles. Sharing benefits and responsibilities equitably supports international justice. Ethical collaboration fosters trust and mutual respect. Continuous ethical review of colonization practices is necessary. Ongoing assessments and adjustments address emerging concerns. Adaptable ethical frameworks respond to new challenges. Educational programs on ethics raise awareness and guide behavior. Teaching ethical considerations fosters a conscientious community. Informed residents uphold the colony's moral standards. Balancing scientific curiosity with ethical responsibility ensures responsible exploration. Respecting Mars' integrity while seeking knowledge benefits all. Ethical exploration supports both discovery and preservation. The impact on the Martian ecosystem is a critical consideration in colonization efforts. Understanding and mitigating these impacts is essential for sustainable living. Responsible practices protect Mars's natural environment. Human activities can disrupt the delicate Martian ecosystem. Introducing Earth-based organisms may have unforeseen consequences. Careful management is required to prevent ecological imbalance. Construction projects alter the Martian landscape. Building habitats, roads, and infrastructure can damage local features. Minimizing land use and employing eco-friendly designs reduce harm. Waste management practices are vital for environmental health. Proper disposal and recycling prevent contamination of soil and water. Effective waste systems protect the ecosystem from pollution. Water extraction must be conducted sustainably. Overuse of local water sources can deplete essential reserves. Balancing water use with natural replenishment is crucial. Agricultural activities impact the Martian soil. Using hydroponics and other soil-free methods can mitigate this effect. Sustainable farming practices ensure long-term soil health. Mining and resource extraction can cause significant disruption. Responsible mining practices and site restoration reduce environmental damage. Sustainable extraction methods protect the ecosystem. Energy production must prioritize environmental preservation. Renewable energy sources like solar and wind have minimal impact. Choosing clean energy supports ecological health. Introducing earth plants and animals requires careful planning. Non-native species can become invasive and disrupt local balance. Controlled introduction and monitoring prevent ecological harm. Scientific research must respect the Martian environment. Field studies and experiments should minimize physical impact. Ethical research practices support both discovery and preservation. Tourism and human activity increase environmental pressure. Managing tourist access and activities helps protect sensitive areas. Sustainable tourism practices balance exploration with conservation. Climate control efforts on Mars have broad ecological implications. Terraforming and atmospheric modifications can drastically alter the ecosystem. Evaluating long-term impacts ensures responsible climate management. Preserving natural landmarks and features maintains Mars's heritage. Protecting significant sites prevents loss of historical and scientific value. Conservation efforts honor the planet's unique characteristics. Continuous monitoring of environmental health is essential. Tracking changes and identifying risks allow for timely intervention. Ongoing assessment supports adaptive management strategies. Global cooperation enhances efforts to protect the Martian ecosystem. Sharing knowledge and resources improves conservation practices. International collaboration ensures comprehensive ecological stewardship. Balancing human needs and planetary health is essential for sustainable colonization. Ensuring the well-being of residents while protecting Mars' environment is a delicate task. Effective strategies can achieve this balance. Habitat design must prioritize both comfort and minimal environmental impact. Eco-friendly materials and efficient construction techniques reduce the ecological footprint. Sustainable living spaces support long-term habitation. Energy needs should be met with renewable sources. Solar and wind energy minimize environmental damage compared to fossil fuels. Renewable energy systems ensure a steady supply without harming Mars. Water use must be efficient and sustainable. Recycling and advanced filtration systems conserve water resources. Balanced water management protects local sources and supports human consumption. Agricultural practices should focus on low-impact methods. Hydroponics and aeroponics reduce soil use and conserve water. Sustainable farming ensures food security while preserving the environment. Waste management is critical for reducing pollution. Comprehensive recycling and waste-to-energy technologies minimize waste. Proper disposal methods protect the Martian ecosystem. Resource extraction should be carefully controlled. Sustainable mining techniques and site rehabilitation reduce environmental degradation. Responsible extraction supports industrial needs without long-term harm. Environmental monitoring systems track the health of Mars's ecosystems. Continuous data collection helps identify and mitigate impacts. Monitoring supports adaptive management practices. Policies must balance development with conservation. Regulations ensure that human activities do not irreparably damage the environment. Effective governance promotes sustainable growth. Educational programs raise awareness about environmental stewardship. Teaching colonists sustainable practices fosters a culture of conservation. Informed residents actively participate in protecting their new home. Research and innovation drive sustainable solutions. Developing new technologies and methods reduces human impact. Continuous improvement supports a balanced approach to colonization. Community involvement in environmental decisions strengthens commitment. Public forums and feedback channels encourage active participation. Engaging the community ensures diverse perspectives are considered. International collaboration enhances sustainability efforts. Sharing expertise and resources fosters global solutions. Cooperation with Earth and other colonies supports planetary health. Emergency preparedness plans address potential environmental crises. Rapid response systems and contingency plans mitigate damage. Preparedness ensures resilience in the face of unforeseen events. Long-term planning integrates human needs with environmental goals. Strategic vision and proactive policies guide sustainable development. Balancing these priorities ensures a thriving, harmonious colony. Long-term environmental strategies are essential for the sustainability of a Mars colony. These strategies ensure that the planet's ecosystem remains healthy and viable. Implementing them requires careful planning and commitment. Developing renewable energy sources is a primary focus. Solar, wind, and nuclear power provide reliable and clean energy. These sources reduce reliance on fossil fuels and minimize environmental impact. Sustainable water management practices are crucial. Advanced recycling systems and efficient usage protocols conserve water. Long-term water strategies ensure that resources remain available for future generations. Implementing zero-waste policies helps minimize environmental degradation. Recycling, composting, and waste-to-energy technologies reduce waste. Achieving zero waste supports a clean and sustainable environment. Preserving natural Martian landscapes is a key objective. Protecting unique geological features and habitats maintains ecological balance. Conservation efforts ensure that Mars's natural beauty is preserved. Reforestation and greening projects enhance the environment. Introducing plant life supports oxygen production and biodiversity. Green spaces contribute to the overall health and well-being of the colony. Regular environmental assessments track the impact of human activities. Monitoring programs identify potential issues and areas for improvement. Ongoing assessments support adaptive management strategies. Developing eco-friendly building materials reduces environmental harm. Using locally sourced and sustainable materials minimizes the ecological footprint. Green construction practices promote long-term sustainability. Encouraging low-impact transportation options helps reduce emissions. Electric vehicles, bicycles, and public transport offer sustainable mobility. These options support a cleaner and healthier environment. Promoting sustainable agriculture practices ensures food security. Techniques like hydroponics and permaculture conserve resources and reduce waste. Sustainable farming supports a stable food supply. And implementing strict pollution controls protects the environment. Regulations on emissions, waste disposal, and industrial activities prevent contamination. Effective pollution controls maintain ecological integrity. International collaboration enhances environmental strategies. Sharing knowledge and resources with other colonies and Earth promotes best practices. Global cooperation supports a unified approach to environmental preservation. Educating the community about sustainability fosters a culture of conservation. Awareness programs and workshops teach residents about eco-friendly practices. An informed community actively participates in protecting the environment. Investing in research and innovation drives sustainable solutions. Developing new technologies and methods addresses environmental challenges. Continuous improvement supports a thriving and resilient colony. Long-term planning integrates environmental goals with development objectives. Strategic policies and vision guide sustainable growth. Balancing these priorities ensures a prosperous future for the Mars colony. We've covered an extensive range of topics essential for the colonization of Mars, from the initial challenges of reaching the red planet to the intricacies of establishing a self-sustaining colony. Each aspect is critical for success. The journey begins with understanding Mars's unique geological features, its climate, and the presence of water, which are all foundational to supporting life. We've delved into the technological marvels required for this mission, including spacecraft, transportation systems, and life support mechanisms. The design and construction of habitats, incorporating both traditional and innovative approaches like inflatable and underground shelters, ensure safety and sustainability for future Martians. Energy sources and storage solutions are pivotal in maintaining a stable environment on Mars. Solar and nuclear energy options provide reliable power, while advanced storage solutions ensure that energy is available when needed. Balancing efficiency and conservation efforts will be key to sustaining the colony. We explored the development of transport networks, essential for both mobility and logistics. This includes rovers, aerial drones, and systems for cargo and supplies, ensuring smooth operations across the Martian landscape. Human mobility and exploration efforts further expand our understanding and utilization of the planet's resources. Economic models, trade, and commerce play a significant role in building a thriving colony. Job creation and a dynamic labor market are crucial for economic independence from Earth, fostering a robust and self-sufficient Martian economy. Funding and investment strategies, combined with innovative economic models, support this growth. Environmental preservation and ethical considerations are at the heart of sustainable colonization. Protecting Mars's ecosystem while meeting human needs is a delicate balance, requiring continuous monitoring and adaptive strategies. Long-term environmental plans ensure that we maintain the health of the planet for future generations. Governance and laws establish a framework for fair and effective management. Social structure and community building initiatives foster a cohesive and supportive society. Cultural and recreational activities enrich life on Mars, promoting well-being and social cohesion. Education and knowledge-sharing drive progress and innovation. Integrating with Earth societies enhances these efforts, ensuring that Mars benefits from global expertise and collaboration. Together, these elements create a vibrant, forward-looking community. Finally, the importance of balancing human needs with planetary health cannot be overstated. Sustainable practices, technological innovation, and international cooperation are key to achieving this balance. Long-term planning and environmental strategies will guide the colony towards a prosperous future. If you enjoyed this video, please like and subscribe to our channel. Check out the rest of our videos for more insights into the fascinating journey of space exploration and the future of humanity on Mars. Your support helps us continue to bring you detailed and engaging content on this incredible topic. Thank you for watching.